Imagine traveling back in time to witness Earth's most incredible secrets. A planet where the sky rained molten rock, where dragonflies had wingspans larger than eagles, and where our ancestors shared the world with rainbow-colored dinosaurs. This is not science fiction. This is the real story of our planet's past. For 46 billion years, Earth has been a stage for the most extraordinary drama ever conceived. From hellish beginnings that would make Venus seem hospitable, to ice ages that froze the entire planet solid, to explosions of life so bizarre they seem like alien invasions. These are the shocking truths that scientists have uncovered, hidden in ancient rocks, preserved in amber, and written in the very atoms of our world. Prepare to discover that reality is far stranger than any fantasy. 1. The birth of hell on Earth. Step back 46 billion years and witness the most violent moment in our planet's history. A rogue planet named Theia, roughly the size of Mars, comes screaming through space at unimaginable speed. The collision that follows isn't just catastrophic. It's apocalyptic beyond human comprehension. When Theia slams into the young Earth, the impact generates surface temperatures of 3,680 degrees Fahrenheit. To truly grasp this hellish heat, imagine that every piece of copper on Earth would instantly melt into liquid puddles. But it gets worse. The atmosphere itself transforms into a nightmarish soup of vaporized rock particles, glowing red-hot and toxic to any conceivable form of life. The entire planet becomes a molten ocean of lava stretching from pole to pole. No solid ground exists anywhere. Earth glows like a demonic star, radiating deadly heat into the vacuum of space, while its surface churns like a cosmic cauldron of liquid fire and destruction. 2. 20 million years of molten terror. For 20 million years, longer than humans have existed as a species, Earth remained trapped in this molten nightmare. Imagine a world where the very concept of ground doesn't exist, where temperatures hover between 1,800 and 2,000 Kelvin, hot enough to vaporize lead and turn diamonds into gas. This isn't just a brief catastrophe. This is Earth's infancy, a period so long that entire mountain ranges could have formed and eroded away on a normal planet. During these endless millennia, our world spins through space as nothing more than a ball of liquid rock and metal. The surface bubbles and churns like cosmic soup, with massive convection currents creating patterns of destruction that dwarf any earthly volcano. Gases that would later become our precious atmosphere remain trapped in the molten chaos below. No weather exists except the eternal storm of heat. No seasons, no day-night temperature variations, just the constant, overwhelming presence of liquid fire that would continue for longer than complex life has existed on Earth. 3. The moon's impossible birth. In just a few hours, one of the most violent events in solar system history creates Earth's eternal companion. When Theia strikes Earth at 20 kilometers per second, that's 45,000 miles per hour, the collision unfolds with such devastating force that both planets simply cease to exist as solid bodies. In mere hours, two entire worlds vaporize into a cloud of superheated gas and debris that stretches across thousands of miles of space. Picture this cosmic destruction. Chunks of molten rock the size of mountains hurtle through space at speeds that would carry you around Earth's equator in just over an hour. The impact site becomes a hellish fountain of vaporized planet, shooting material far beyond what would become the moon's orbit. From this chaos, gravity begins its patient work. Slowly, the scattered debris starts to coalesce. The largest chunks attract smaller ones, and within those few crucial hours, the moon begins to form, not as a gentle accretion over millions of years, but as a rapid, violent birth from the ashes of two destroyed worlds. 4. When planets turn to vapor. The Theia impact achieves something so extreme it challenges our understanding of matter itself. It vaporized entire planets. When the collision occurred, both Earth and Theia didn't just melt or fragment. They transformed into a rock vapor atmosphere that stretched across space like a ghostly, superheated fog of planetary remains. Every molecule that had once formed mountains, valleys, and the cores of two worlds now floated as gas in the emptiness between them. This vaporization created temperatures so extreme that solid matter simply couldn't exist. Imagine every grain of sand, every pebble, every boulder on two entire planets transformed into invisible gas, glowing with heat that would make the surface of the sun seem cool by comparison. For 1,000 years, this planetary fog slowly condensed back into solid matter. Gradually, drop by drop, the vapor transformed back into molten rock that would eventually become the Earth and Moon we know today. It was like watching two worlds literally evaporate and then rain back into existence over a millennium of patient cosmic reconstruction. 5. The Moon's crushing embrace. In the aftermath of this cosmic catastrophe, the newly formed Moon hung in Earth's sky like a looming giant of destruction. At only 15,000 miles away, less than 1/15th its current distance, the Moon dominated the heavens as a massive, threatening presence. To put this in perspective, if you could see the Moon today at this distance, it would appear 15 times larger in the sky, covering an area equivalent to your outstretched hand. The gravitational forces generated by this proximity were absolutely crushing. Tides of molten rock hundreds of feet high swept across Earth's surface in endless, devastating cycles. The Moon's pull was so intense that it literally kept both worlds molten for millions of years, preventing any possibility of cooling or solidification. These weren't gentle ocean tides. There were tsunamis of liquid rock that could have swallowed entire mountain ranges. The constant flexing and stretching of both bodies created friction heat that maintained the hellish temperatures long after the initial impact energy should have dissipated. Earth and Moon remained locked in a dance of mutual destruction, each preventing the other from finding peace. 6. When days lasted hours. In those chaotic early moments, Earth spun with such ferocious speed that a complete day-night cycle lasted just 2 to 3 hours. Imagine experiencing sunrise, noon, sunset, and midnight in less time than it takes to watch a movie. The impact that created the Moon had sent Earth spinning like a cosmic top, rotating so rapidly that the very concept of day and night became almost meaningless. If you could somehow stand on this hellish surface, you'd watch the sun race across the sky faster than the hour hand on a clock. This frantic rotation created its own brand of chaos. The centrifugal force from spinning so quickly would have made you feel substantially lighter at the equator, while the constantly changing position of the sun created a strobing effect of light and shadow that cycled relentlessly. Over millions of years, the Moon's gravitational pull acted like a cosmic brake, gradually slowing Earth's rotation through tidal friction. Each passing day became slightly longer as our planet's rotational energy transferred to the Moon, pushing our satellites slowly outward while giving us the familiar 24-hour day we know today. 7. Oceans in Hell. Here's where the story takes an impossible turn. Somehow, impossibly, liquid water existed on this molten nightmare. Chemical analysis of 4404-billion-year-old zircon crystals discovered in Western Australia has revealed one of geology's most shocking secrets. These ancient time capsules contain chemical signatures that could only form in the presence of liquid water. This means that just 160 million years after the moon-forming impact, a geological instant, oceans somehow existed on Earth's surface. How could liquid water survive on a world that was supposedly too hot for anything but molten rock? The answer challenges everything we thought we knew about early Earth. Perhaps the planet cooled far more rapidly than expected, or maybe water found refuge in protected basins while the rest of the world remained molten. These weren't the vast, blue oceans we know today. They were likely small, isolated pools of scalding water, barely clinging to existence on a world still dominated by lava flows and volcanic chaos. Yet somehow, against all odds, these precious puddles of H2O managed to persist in the hellscape of early Earth. 8. Life's impossible beginning. Even more shocking than the early oceans is the possibility that life itself began during this supposed lifeless period. Scientists studying those same 41-billion-year-old zircon crystals have found potential evidence of biological activity. Carbon signatures that suggest living organisms may have existed during the Hadean Eon, Earth's period of supposed lifelessness. If confirmed, this would mean life emerged not in some peaceful, Eden-like environment, but in the cosmic equivalent of hell itself. Picture the first living cells somehow finding a way to survive in a world of constant volcanic eruptions, acid rain, and temperatures that would instantly kill any modern organism. These weren't just hardy bacteria. They were the ultimate extremophiles, capable of thriving in conditions that would make the inside of an active volcano seem hospitable. This discovery suggests that life doesn't need perfect conditions to begin. It needs any conditions at all. Perhaps life is so tenacious, so determined to exist, that it can emerge even in the most hostile environments imaginable. These ancient microbes were literally forged in fire, setting the stage for billions of years of evolutionary resilience. 9. The Cosmic Shooting Gallery. As if the hellish conditions weren't enough, early Earth existed in a cosmic shooting gallery where massive asteroids rained down with terrifying frequency. During the late heavy bombardment, asteroid impacts occurred 10 times more frequently than scientists previously estimated. This wasn't occasional cosmic bad luck. This was a sustained assault from space that turned Earth into a target in an interplanetary firing range. Every few million years, another mountain-sized chunk of rock would come screaming out of the darkness to deliver fresh devastation. These impacts weren't just local disasters. They were global catastrophes that could reset the entire planet's development. Each major collision sent shockwaves around the world, triggered massive volcanic eruptions, and filled the atmosphere with debris that blocked out the sun for years at a time. The frequency was so intense that any complex life trying to evolve would face constant extinction. It was like trying to build a sandcastle while someone repeatedly hits it with sledgehammers. Yet somehow, in the brief periods between these cosmic disasters, life not only persisted but began the long journey toward complexity. 10. Catastrophe every 15 million years. The bombardment followed a devastating pattern. Impacts the size of the one that killed the dinosaurs occurred every 15 million years. To understand this frequency, consider that the Chicxulub asteroid that ended the age of dinosaurs was a global catastrophe that triggered mass extinction. Now imagine that level of devastation happening every 15 million years, roughly 300 times throughout Earth's history. Each impact delivered the explosive force of millions of nuclear weapons, creating global firestorms and climate chaos. These weren't random events scattered throughout time. They followed a cosmic rhythm of destruction that kept early Earth in a constant state of reset. Just as life might begin to establish complex ecosystems, another planetary-scale disaster would wipe the slate clean and force evolution to start over. The late heavy bombardment was like Earth's violent adolescence, a period when our planet couldn't catch a break from cosmic bullying. Mountains formed only to be shattered by the next impact. Oceans boiled away and reformed multiple times. Any organisms that survived these repeated catastrophes were the ultimate survivors, tested by fire and forged by repeated near-extinction events. 11. Boiling away the oceans. Individual asteroid impacts were so powerful they could literally boil away 100 meters of the entire global ocean while raising atmospheric temperatures to 932 degrees Fahrenheit. Imagine an impact so violent that it doesn't just create a crater. It vaporizes a layer of ocean 300 feet deep across the entire planet. The energy required is almost incomprehensible. Enough heat to turn millions of cubic miles of water into superheated steam that rises into the atmosphere like a planet-wide pressure cooker explosion. The atmospheric temperature spike to 932 degrees Fahrenheit would have created a greenhouse effect so extreme that Earth temporarily became more like Venus. Any surviving organisms would have faced not just the initial impact, but months or years of oven-like conditions that would cook everything on the surface. These events created a cycling pattern of oceanic destruction and reformation. Water would boil away into space, then gradually return as the planet cooled, only to be boiled away again by the next major impact. Early Earth experienced the complete loss and reformation of its oceans multiple times, each cycle erasing any biological progress that might have accumulated over millions of years. 12. The California-sized crater. One confirmed impact from this period created a crater nearly 500 kilometers across, larger than the entire state of California. Picture a hole in the ground so vast that you could drop the entire state of California into it and still have room left over. This wasn't just a crater. It was a wound in the planet so deep and wide that it fundamentally altered Earth's geography for millions of years. The excavated material would have been hurled hundreds of miles in every direction, creating a debris field the size of several states. The impact that created this monster crater released energy equivalent to the explosion of millions of nuclear weapons simultaneously. The shockwaves would have triggered earthquakes and volcanic eruptions on the opposite side of the planet. Debris thrown into space would have created a temporary ring system around Earth, while larger chunks eventually rained back down as a secondary bombardment. For centuries after the impact, this giant crater would have served as a collecting basin for water and sediment, gradually filling in to become a massive inland sea. The geological disruption was so severe that traces of this ancient catastrophe can still be detected in some of the world's oldest rock formations. 13. Life's first act of genocide. In one of history's greatest ironies, the emergence of life triggered Earth's first environmental disaster through an act of biological terrorism that nearly ended everything. Around 24 billion years ago, tiny cyanobacteria began producing a waste product that was absolutely toxic to virtually every living thing on Earth: oxygen. To understand how revolutionary and deadly this was, imagine if a new type of bacteria suddenly started pumping poison gas into our atmosphere. That's exactly what happened, except the poison was the very gas we now depend on for survival. Before this biological catastrophe, Earth's atmosphere contained virtually no free oxygen. Most life forms were adapted to survive in this oxygen-free world, using chemical processes that would be instantly poisoned by oxygen exposure. When cyanobacteria began their photosynthetic revolution, they essentially turned the entire atmosphere into a toxic wasteland for existing life. The result was a mass extinction so severe it makes the dinosaur extinction look mild by comparison. Over 80% of all life forms on Earth died from oxygen poisoning, making this the first and perhaps most devastating example of biological warfare in our planet's history. 14. The oxygen apocalypse. The Great Oxidation Event stands as the most severe biological catastrophe in Earth's history, eliminating over 80% of all living organisms through atmospheric poisoning. This wasn't a quick disaster. It was a slow-motion apocalypse that unfolded over hundreds of millions of years. As oxygen levels gradually rose from virtually zero to significant concentrations, entire ecosystems collapsed in chain reaction extinctions. Bacteria that had thrived for billions of years in oxygen-free environments suddenly found their world transformed into a toxic wasteland. The death toll was unprecedented. Imagine if 80% of all species on Earth today, every mammal, bird, fish, insect, and plant, suddenly died from breathing the air. That's the scale of devastation that early life faced as oxygen levels rose. The only survivors were organisms that either lived in oxygen-free refuges like deep ocean sediments, or those that evolved rapid tolerance to this new atmospheric poison. Yet from this biological holocaust emerged one of evolution's greatest innovations: organisms that could not just tolerate oxygen, but use it to generate far more energy than ever before possible. The Great Oxidation Event was both life's greatest catastrophe and its greatest opportunity, setting the stage for the complex, oxygen-breathing life forms that would eventually include us. 15. How life froze its own planet. In an act of environmental self-destruction that makes modern climate change seem trivial, life literally froze its own planet by accidentally destroying the atmosphere. The oxygen produced by cyanobacteria didn't just poison other organisms. It chemically reacted with methane in the atmosphere, destroying this powerful greenhouse gas and plunging Earth into the most severe ice age in its history. Methane is roughly 25 times more effective than CO2 at trapping heat, so removing it from the atmosphere was like turning off Earth's global heating system. As oxygen levels rose and methane concentrations plummeted, global temperatures crashed with devastating speed. Within a few million years, geological fast-forward, Earth transformed from a warm, habitable world into a frozen snowball where ice covered the entire planet from pole to pole. This was the Huronian glaciation, and it lasted for an almost incomprehensible 300 million years. The organisms that had caused this catastrophe, by producing oxygen, found themselves trapped in a world of their own making. They had essentially committed planetary suicide, creating an ice age so severe that their own survival was threatened. It's the ultimate cautionary tale about unintended consequences of biological activity. 16. Life's ultimate extremists. The organisms that survived Earth's early catastrophes developed survival capabilities so extreme they seem like science fiction made real. Modern extremophile bacteria can survive conditions that would instantly crush a car, freeze solid at temperatures approaching absolute zero, or boil alive in heat that would melt lead. They thrive in pressures over 1,000 times greater than atmospheric pressure. Imagine the weight of a 10-story building pressing down on every square inch of your body. These microbes not only survive such conditions, they prefer them. Temperature extremes that would kill any complex life form are comfortable homes for these biological marvels. Some species happily reproduce in environments colder than liquid nitrogen, while others thrive in water so hot it would instantly vaporize on Earth's surface. They live in acid more corrosive than car battery fluid, in salt concentrations that would mummify any normal organism, and in radioactive environments that would be lethal to humans in minutes. Perhaps most incredibly, some extremophiles can survive direct exposure to the vacuum of space, enduring radiation levels that would sterilize a spacecraft. These organisms represent life's ultimate insurance policy, proof that biology can adapt to literally any environment the universe can create. 17. Earth's first skyscrapers. Long before humans built cities, cyanobacteria constructed Earth's first towering structures, stromatolites that reach heights of 16 to 20 feet. Picture ancient coastlines dominated not by coral reefs or kelp forests, but by massive, layered rock structures built entirely by microscopic organisms. These bacterial cities represented some of the most ambitious construction projects in early Earth's history, built grain by grain over thousands of years by communities of cyanobacteria working in perfect coordination. Each stromatolite was essentially a living skyscraper, with different bacterial communities occupying different floors based on their tolerance for light, oxygen, and other environmental factors. The bacteria would trap sediment particles and precipitate minerals from seawater, gradually building upward toward the sun in slow-motion construction projects that span millennia. These weren't random piles of rock. They were sophisticated biological structures with internal organization, water circulation systems, and specialized zones for different bacterial functions. Some stromatolites developed complex branching patterns, while others grew in perfect dome shapes. They were Earth's first attempt at urban planning, created by organisms so small you'd need a microscope to see individual residents, yet collectively capable of building structures that dominated entire landscapes. 18. The oxygen ares that changed everything. For over 2 billion years, stromatolites served as Earth's primary oxygen production facilities, literally creating the atmosphere we breathe today. These bacterial cities were essentially massive, biological solar panels that captured sunlight and converted it into chemical energy while releasing oxygen as a waste product. But unlike human factories that last decades, these living structures operated continuously for billions of years, slowly but steadily transforming Earth's atmosphere from a toxic, oxygen-free environment into one capable of supporting complex life. The scale of their operation was staggering. Imagine every single breath you take traced back to these ancient bacterial communities. Every oxygen molecule that keeps you alive was likely processed through one of these stromatolite cities during the vast epochs when they dominated Earth's coastlines. During their golden age, stromatolites faced no competition and no predators. They were the only game in town, free to spread across every available coastline and perfect their atmospheric engineering project. Their success was so complete that they fundamentally altered the chemistry of an entire planet, setting the stage for every oxygen-breathing organism that would follow, including eventually us. 19. The planet that became a snowball. During the most extreme climate events in Earth's history, the entire planet, including the equator, was covered in ice up to 1 kilometer thick. Imagine Earth as a giant snowball floating through space, with frozen oceans, ice-covered continents, and temperatures so cold that even the tropical regions were buried under glaciers thicker than the tallest skyscrapers. This wasn't just an ice age. This was complete planetary refrigeration that turned Earth into the solar system's largest ice cube. The ice was so thick that in many places, you could have stacked 3 Empire State Buildings on top of each other and still not reach the surface. Sunlight reflected off the white ice surface instead of being absorbed, creating a runaway cooling effect that kept the planet frozen in its own cosmic freezer. Yet somehow, beneath this planetary ice cap, life persisted. In hidden pockets around hydrothermal vents, in caves beneath the ice, and in tiny meltwater pools, organisms continued their patient struggle for survival. They evolved antifreeze proteins, developed new metabolic pathways that worked at sub-zero temperatures, and learned to extract energy from chemical reactions that didn't require sunlight. These snowball Earth survivors were evolution's ultimate winter athletes. 10 million years of frozen hell. The snowball Earth events lasted up to 10 million years, with global average temperatures plummeting to minus 58 degrees Fahrenheit, turning our planet into a cosmic ice cube. To comprehend this duration, consider that all of human civilization, from the first cities to space travel, has occurred in less than 10,000 years. The snowball Earth periods lasted 1,000 times longer than all of recorded human history. For comparison, if human civilization were a single day, these ice ages would last nearly 3 years. During these frozen epochs, global average temperatures were colder than Antarctica in winter. Even the equator, normally Earth's warmest region, experienced temperatures that would make a deep freeze seem tropical. The ice was so persistent that it created its own weather systems, with massive ice storms and winds that howled across empty, frozen landscapes. But perhaps most remarkably, these weren't just single events. Earth experienced multiple snowball episodes, suggesting that our planet has a tendency toward extreme climate states. Each time, it took millions of years and massive volcanic eruptions to pump enough greenhouse gases into the atmosphere to finally melt the global ice cap and restore liquid oceans. 21. Life's incredible persistence. Even during complete planetary freezing, life found ways to survive in hidden refuges, proving biology's ultimate determination to persist against impossible odds. While most of Earth lay buried under kilometers of ice, life retreated to some of the most extreme refuges imaginable. Around hydrothermal vents on the ocean floor, communities of organisms thrived in pockets of warmth that created underwater oases in the frozen world. These vents, heated by Earth's internal energy, created tiny tropical zones beneath the ice where temperatures could reach hundreds of degrees. In underground caves and beneath thick ice sheets, other organisms develop survival strategies that border on the miraculous. Some bacteria learn to slow their metabolism to almost nothing, essentially hibernating for millions of years while waiting for better conditions. Others develop the ability to use chemical energy instead of sunlight, creating entirely new ecosystems that operated like alien worlds. Perhaps most incredibly, some life forms found refuge in thin films of liquid water that existed between ice crystals, exploiting microscopic environments that were barely large enough to house single cells. These organisms prove that life doesn't need comfortable conditions. It just needs any opportunity at all, no matter how tiny or hostile. 22. Evolution's greatest mystery. The Cambrian explosion represents the most dramatic and mysterious event in the history of life. The sudden appearance of complex organisms in just 13 to 25 million years. For most of Earth's history, life remained stubbornly simple. For over 3 billion years, the most complex organisms were single-celled bacteria and basic multicellular formations like stromatolites. Then, approximately 5,388 million years ago, something unprecedented happened. Life suddenly exploded into complexity with a creativity and speed that continues to baffle scientists. In what amounts to an evolutionary eye blink, virtually every major animal body plan appeared in the fossil record. Creatures with shells, spines, eyes, legs, tentacles, and internal organs materialized as if someone had flipped a switch labeled complexity. The diversity was so extreme that many Cambrian organisms look more like alien life forms than anything related to modern animals. This wasn't gradual change. This was biological revolution. Within 25 million years, evolution invented solutions to problems of movement, feeding, defense, and reproduction that had never existed before. Eyes evolved from simple light-sensing spots to complex compound structures. Hard shells appeared to protect soft bodies. Predator-prey relationships developed, creating the first biological arms race and setting patterns that continue today. 23. The nightmare shrimp. Anomalocurus canadensis ruled Cambrian seas as a 3-foot-long apex predator, so alien-looking that scientists initially mistook its body parts for 3 different animals. Picture a creature that seems assembled from the parts bin of a science fiction movie. A flexible, segmented body like a swimming rug, 2 massive grasping arms lined with sharp spines, and compound eyes the size of dinner plates. This was Anomalocurus, whose name literally means anomalous shrimp. Though it was neither anomalous nor a shrimp, it was the Cambrian Ocean's ultimate killing machine. The creature's feeding appendages were so large and fearsome that early paleontologists thought they were separate animals, giant shrimp-like creatures. The circular mouth was initially classified as a jellyfish, while the body segments were described as yet another mysterious organism. Only when complete specimens were discovered did scientists realize they were looking at parts of a single, impossible predator. Anomalocurus hunted using vision systems more sophisticated than most modern arthropods. Its massive compound eyes contained over 16,000 individual lenses, giving it panoramic, high-resolution vision that could detect the slightest movement in the murky Cambrian seas. When it spotted prey, those powerful front appendages would snap forward like mechanical claws, grasping victims in an embrace of sharp spines before delivering them to its crushing circular mouth. 24. Eyes like ancient supercomputers. Anomalocurus possessed the most advanced vision system of its time, with compound eyes containing 16,000 individual lenses, more complex than most modern arthropods. Each eye was essentially a biological supercomputer capable of processing visual information from thousands of different angles simultaneously. Modern dragonflies, considered to have excellent vision, typically have around 12,000 to 16,000 lenses per eye. This means Anomalocurus had vision comparable to one of today's most visually sophisticated predators, despite living over 500 million years ago. The sophistication of these eyes suggests that Anomalocaris was an active, intelligent hunter rather than a simple scavenger. The ability to process complex visual information from multiple sources simultaneously would have given it an enormous advantage in the Cambrian seas, where most other organisms had simple light-detecting spots or no vision at all. This advanced vision system appeared suddenly in the fossil record with no apparent evolutionary predecessors, adding to the mystery of the Cambrian explosion. How did such sophisticated eyes evolve so quickly? The answer remains one of paleontology's greatest puzzles, suggesting that evolution can achieve in millions of years what we might expect to take hundreds of millions. 25. The upside-down nightmare. Hallucigenia was so bizarre that when scientists first reconstructed it, they literally built it upside down, unable to determine which end was the head. When paleontologists first discovered Hallucigenia fossils in the 1970s, the creature was so alien that they couldn't figure out basic anatomy. They initially reconstructed it walking on its defensive spines, essentially building a model that was walking on its back with its legs in the air. The mistake wasn't corrected until the 1990s when better fossils revealed the true orientation. Even when properly oriented, Hallucigenia remains one of evolution's strangest experiments. The creature resembled a walking pincushion with a serious attitude problem, covered in sharp defensive spines along its back and equipped with simple walking legs underneath. But the really bizarre features were at the feeding end. A proboscis-like head with a circular mouth lined with multiple rows of tiny teeth. The name Hallucigenia was chosen because the creature looked so much like a hallucination that scientists weren't sure it could be real. Its combination of features, spines, legs, feeding apparatus, and overall body plan didn't match any known animal group, making it a true evolutionary orphan that challenges our understanding of how complex body plans develop. 26. A mouth full of horror. Hallucigenia possessed one of the most nightmarish feeding systems ever discovered. Needle-like teeth that extended past its jaw and continued down its throat. The creature's mouth was essentially a biological food processor designed for maximum efficiency and minimum escape chances for prey. The circular opening was lined with multiple rows of sharp, inward-pointing teeth that made retreat impossible for anything unlucky enough to be caught. But the horror didn't stop at the mouth. The teeth continued down the throat, creating a one-way digestive tunnel lined with needles. This feeding system suggests that Hallucigenia was likely a filter feeder or scavenger that processed large amounts of organic material, straining nutrients from seawater or mud. The multiple rows of throat teeth would have ensured that nothing edible escaped once it entered the creature's digestive system. The defensive spines along its back served as protection while feeding, allowing Hallucigenia to browse for food without worrying about attacks from above. This combination of offensive feeding apparatus and defensive protection made it one of the Cambrian's most successful survivors, even if it looked like something from a nightmare. 27. The five-eyed joke. Opabinia was so impossible-looking that when it was first presented at a scientific conference in 1972, the audience burst into laughter, thinking it was a paleontological joke. Picture a creature that seems designed by committee after everyone involved had been drinking. 5 mushroom-shaped eyes mounted on stalks, a backwards-facing mouth, and a long, flexible proboscis tipped with a grasping claw. To make matters worse, the entire body was segmented but didn't match any known animal pattern. Scientists literally didn't know what to make of it. The reaction at the 1972 conference was understandable. Opabinia looked like something a child might draw after being asked to design the strangest animal possible. The 5 eyes on stalks gave it an almost comical appearance, while the backwards mouth suggested that evolution had somehow installed its head facing the wrong direction. But as more specimens were discovered, it became clear that Opabinia wasn't a mistake or a joke. It was a real animal that had lived successfully in Cambrian oceans for millions of years. The bizarre combination of features actually made sense. The stalked eyes provided panoramic vision, The flexible proboscis could probe into crevices for food, and the backwards mouth was positioned to receive prey captured by the grasping claw. 28. The alien probe. Opabinia's most distinctive feature was its flexible proboscis, 4 times longer than its head and tipped with a mechanical-looking claw for capturing prey. This wasn't just a simple feeding tube. It was a sophisticated biological tool that could extend, contract, and flex in multiple directions like a tentacle with built-in grabbing power. The proboscis was so flexible that Opabinia could bend it back over its head to deliver captured prey to its backwards-facing mouth, creating a feeding system unlike anything seen before or since. The claw at the tip wasn't just a simple pincer. It was a complex grasping mechanism with multiple parts that could open and close with precision. This suggests that Opabinia was a selective feeder, capable of picking individual prey items from the seafloor or plucking them from the water column with surgical accuracy. The entire feeding system worked like a biological crane, with the 5 stalked eyes providing the visual guidance needed to operate the proboscis with precision. This combination of advanced vision and sophisticated manipulation tools made Opabinia one of the Cambrian's most technologically advanced predators, even though its appearance was utterly alien by modern standards. 29. The perfect fossil laboratory. The Burgess Shale preserves over 65,000 specimens in exquisite detail, representing the most complete record of soft-bodied Cambrian life ever discovered. What makes the Burgess Shale extraordinary isn't just the number of fossils, but their incredible preservation. Normally, only hard parts like shells and bones survive fossilization, but the Burgess Shale captures everything: soft tissues, internal organs, digestive systems, and even the contents of ancient stomachs. It's like having a perfectly preserved snapshot of an entire Cambrian ecosystem. This remarkable preservation occurred through a geological accident of perfect timing. Underwater avalanches swept down the continental slope, instantly burying entire communities of marine organisms in fine mud that excluded oxygen and prevented decay. The creatures were essentially freeze-dried in stone, maintaining their 3-dimensional structure and microscopic details for over 500 million years. The diversity preserved in the Burgess Shale reads like a catalog of evolutionary experiments. Many organisms represent body plans that were tried once and never repeated. Evolutionary dead, ends that show us alternative paths life might have taken. Others are clearly related to modern groups, but display features so bizarre they challenge our understanding of how familiar animals evolve their current forms. 30. The car-sized millipede. Arthropleura reached lengths of 85 feet and weighed 110 pounds, making it the largest arthropod ever to walk the earth, essentially a millipede the size of a small car. Imagine encountering this massive creature in a carboniferous forest, longer than a king-size bed and heavier than a large dog, but with the body plan of a millipede. Arthropleura represents the absolute extreme of arthropod gigantism, growing to sizes that challenge our understanding of how segmented animals can function. The creature's sheer bulk required sophisticated engineering solutions. Its exoskeleton had to be thick enough to support tremendous weight while remaining flexible enough for movement. The internal breathing system had to deliver oxygen to massive body segments, while the nervous system had to coordinate hundreds of legs working in perfect synchronization. Recent 2023 research has revealed that Arthropleura possessed compound eyes, a feature completely unknown in modern millipedes. This suggests the giant was more active and visually oriented than its smaller descendants. The combination of size, vision, and mobility made Arthropleura one of the Carboniferous period's most dominant land animals, capable of rearing up on its hind legs to reach vegetation several feet off the ground. 31. Eyes where they shouldn't be. Arthropleura possessed compound eyes, a stunning feature that no modern millipede has, suggesting these giants were far more sophisticated than their descendants. This discovery completely overturns our understanding of millipede evolution and behavior. Modern millipedes are essentially blind, relying on touch and chemical senses to navigate their world. They're typically secretive creatures that avoid light and spend most of their time in soil or leaf litter. But Arthropleura's compound eyes suggest a completely different lifestyle. The presence of sophisticated vision systems indicates that these giants were active, visually oriented animals that relied on sight for navigation, feeding, and possibly predator avoidance. They may have been active during daylight hours, roaming openly through carboniferous forests rather than hiding in the undergrowth like their modern relatives. This evolutionary reversal, where ancient species had more advanced features than their descendants, challenges common assumptions about evolutionary progress. Arthropleura represents a peak of millipede evolution that was never again achieved, suggesting that sometimes evolution moves backwards, trading sophisticated features for other advantages as environmental conditions change. 32. Hawks of the Carboniferous. Meganeura dragonflies dominated Carboniferous skies with wingspans of 28 inches, larger than modern hawks and terrorizing aerial ecosystems for over 50 million years. These weren't just large dragonflies. They were flying predators that ruled their environment as completely as modern birds of prey. With wingspans approaching 3 feet, Meganeura could soar over Carboniferous forests like feathered raptors, using their massive compound eyes to spot prey from considerable distances. The hunting capabilities of these giant dragonflies were extraordinary. Modern dragonflies are already among the most efficient aerial predators, with success rates approaching 95% when attacking prey. Meganeura would have been even more formidable, capable of taking down prey much larger than anything modern dragonflies could handle. For over 50 million years, longer than mammals have dominated the land, these aerial giants were the undisputed masters of the sky. They witnessed the rise and fall of entire forest ecosystems, surviving through multiple climate changes and evolutionary transitions while maintaining their position as apex aerial predators. Their eventual extinction marked the end of an era when insects ruled the air with the same dominance that birds enjoy today. 33. The hyperoxic atmosphere. Atmospheric oxygen levels reached 30 to 35% during the Carboniferous period, creating an environment significantly richer in oxygen than today's 21%. To understand what this hyperoxic world felt like, imagine breathing air so rich in oxygen that every breath supercharged your cells with energy. For humans, prolonged exposure to 35% oxygen would cause oxygen toxicity, leading to lung damage and potentially fatal complications. But for Carboniferous organisms adapted to these conditions, it was like living in a natural performance-enhancing environment. This oxygen-rich atmosphere was created by the massive forests of the Carboniferous period. Trees and plants pumped oxygen into the air faster than natural processes could remove it, creating a runaway effect that pushed atmospheric oxygen to levels never seen before or since. The excess oxygen created a feedback loop where fires burned hotter and more frequently, while organisms grew to unprecedented sizes. The hyperoxic environment affected everything from forest fire patterns to animal metabolism. Wildfires could burn with such intensity that they consumed entire forest systems, while the abundant oxygen enabled rapid growth and gigantic body sizes in animals that could efficiently process the gas-rich air. 34. An ecosystem of giants. The hyperoxic Carboniferous atmosphere produced a menagerie of massive arthropods, including 6-foot-long poisonous centipedes, 3-foot-long scorpions, and cockroaches the size of house cats. This wasn't just isolated gigantism. It was an entire ecosystem scaled up to nightmarish proportions. Every arthropod group seemed to push the boundaries of size, creating a world where familiar creatures became monsters. The 6-foot centipedes were venomous predators capable of taking down prey much larger than modern centipedes could handle, while 3-foot scorpions used their massive claws and stingers to dominate terrestrial food webs. Even the humble cockroach joined the gigantism trend, growing to sizes that would make them formidable predators rather than scavengers. House cat-sized cockroaches with powerful jaws and robust legs would have been active hunters rather than the secretive creatures we know today. This size inflation affected the entire food web structure. Predator-prey relationships were recalibrated around massive arthropods, while competition for resources occurred between creatures that would seem mythological by modern standards. The Carboniferous forests weren't just larger than today's ecosystems. They were populated by animals that belonged in science fiction movies. 35. The yard-long killer. Pulmonoscorpius reached a yard in length and possessed venom potent enough to kill prey much larger than anything modern scorpions could handle. Imagine a scorpion the length of a baseball bat, with claws powerful enough to crush bones and a stinger capable of delivering venom in quantities that would be lethal to animals the size of dogs or larger. Pulmonoscorpius wasn't just a scaled-up version of modern scorpions. It was an entirely different class of predator. The venom delivery system had to be correspondingly massive to affect large prey. While modern scorpions use relatively small amounts of venom to subdue insects and small vertebrates, Pulmonoscorpius could inject venom loads comparable to those of large snakes. The stinger itself was a formidable weapon even without venom, sharp enough and strong enough to pierce thick arthropod exoskeletons. These giant scorpions likely occupied the ecological niche filled by large mammalian predators today. They were probably ambush predators that waited in Carboniferous undergrowth for suitable prey to pass within range of their massive claws. Once grasped, few creatures would have been able to escape the combined assault of crushing claws and massive venom doses. 36. Growing big to survive poison. Recent research reveals that young insects actually grew larger to avoid oxygen toxicity, not just to benefit from abundant oxygen, showing that gigantism was partly a survival strategy. This discovery completely changes our understanding of Carboniferous gigantism. Rather than simply growing large because oxygen was abundant, insects were actually trying to protect themselves from oxygen poisoning. Higher oxygen levels can be toxic, causing cellular damage through oxidative stress, the same process that causes aging in modern organisms. Larger body size provided protection by diluting oxygen concentration and reducing the surface area to volume ratio where oxygen absorption occurs. Young insects that grew quickly to large sizes were essentially outrunning oxygen toxicity, while those that remained small were more vulnerable to cellular damage from hyperoxic conditions. This survival strategy created an evolutionary arms race toward larger size, where insects had to grow big or die from oxygen poisoning. The result was an entire ecosystem of giants, all trying to survive in an atmosphere that was simultaneously beneficial and toxic. When oxygen levels eventually dropped, the giants could no longer maintain their size and gradually evolved back towards smaller forms. 37. Earth's closest call with death. The Permian-Triassic extinction 252 million years ago eliminated 96% of marine species and 70% of terrestrial vertebrates, representing Earth's closest approach to total biological sterilization. This wasn't just another mass extinction. It was a near-total reset of life on Earth that came terrifyingly close to ending the entire biological experiment. To put the devastation in perspective, imagine if 96% of all marine life died today. Every whale, dolphin, fish, and coral reef reduced to scattered survivors clinging to existence in isolated refuges. The extinction was so severe that it took over 10 million years for biodiversity to recover to pre-extinction levels, and many ecosystems never returned to their original complexity. Entire groups of organisms that had dominated Earth for millions of years simply vanished forever, leaving behind only fossils as evidence of their existence. What makes this extinction even more terrifying is how close it came to complete sterilization. Scientists estimate that if the crisis had been just slightly more severe or had lasted a bit longer, complex life might have ended entirely. Earth could have reverted to a bacterial world, setting back the evolution of complex organisms by hundreds of millions of years. 38. Death in a geological instant. The Great Dying occurred in less than 100,000 years, possibly as quickly as 20,000 years, a camera shutter click on geological timescales. When paleontologists talk about gradual geological processes, they typically mean changes that occur over millions of years. But the Permian extinction happened so fast that on Earth's timescale, it was essentially instantaneous. New radiometric dating techniques have revealed that the crisis unfolded faster than previously imagined. To understand this speed, consider that 100,000 years represents less than 0.0002% of Earth's history. If Earth's entire 46 billion year history were compressed into a single year, the Great Dying would have lasted less than 11 minutes. And if the most rapid estimates of 20,000 years are correct, the extinction would have been over in just 2 minutes of Earth time. This incredible speed meant that organisms had virtually no time to adapt or evolve resistance to the changing conditions. Evolution typically requires thousands of generations to produce significant adaptations, but the Permian crisis unfolded faster than most species could respond. It was like trying to evolve while being hit by a freight train. 39. The volcanic apocalypse. Global temperatures rose by 10 to 15 degrees Celsius during the Great Dying, while massive volcanic eruptions created acid rain that dissolved marine organisms and turned oceans into acidic death traps. The temperature increase wasn't gradual warming. It was rapid planetary heating that turned Earth into a global oven. An increase of 10 to 15 degrees Celsius represents a temperature spike that would make modern climate change seem trivial by comparison. To put this in perspective, human civilization has never experienced a temperature change of more than 2 to 3 degrees Celsius. And scientists warn that even a 4 degrees Celsius increase would be catastrophic for modern ecosystems. The volcanic eruptions that caused this heating weren't ordinary volcanoes. They were massive outpourings of lava that lasted for hundreds of thousands of years. The Siberian Traps eruptions released gases that not only warmed the planet, but also created acid rain so corrosive it could dissolve shells and skeletons of marine organisms. Ocean chemistry changed so dramatically that seawater became toxic to most marine life. The combination of heat, acidity, and chemical poisoning created aquatic environments that were essentially uninhabitable. Fish, corals, and marine invertebrates faced a triple assault of environmental changes that overwhelmed their ability to survive. 40. A continent of lava. The Siberian Traps volcanic eruptions released enough lava to bury the entire continental United States under hundreds of feet of molten rock. To visualize this scale of volcanic activity, imagine every state from California to Maine, from Florida to Alaska, covered in lava flows several stories deep. The total volume of erupted material exceeded 1 million cubic miles, enough molten rock to bury the entire state of Texas under a layer of lava more than 5 miles thick. These weren't explosive eruptions like Mount St. Helens. They were massive outpourings of flood basalt that continued for hundreds of thousands of years. The lava didn't just flow from single volcanic peaks, but erupted from massive fissures that stretched for hundreds of miles across Siberia. It was like the earth split open and bled molten rock across an area larger than most countries. The environmental impact extended far beyond the immediate lava flows. The eruptions released massive amounts of sulfur dioxide, carbon dioxide, and other gases that poisoned the atmosphere and triggered the runaway greenhouse effect that drove global temperatures to lethal levels. The Siberian Traps represent volcanic activity on a scale that modern humanity has never witnessed and hopefully never will. 41. Death metal poisoning. Nickel aerosols from Siberian volcanoes fed methane-producing archaea, creating a runaway greenhouse effect that amplified the extinction through toxic metal contamination. This discovery reveals one of the most diabolical mechanisms in Earth's history: how volcanic eruptions created a biological feedback loop that made the extinction far worse than it should have been. The Siberian eruptions didn't just release lava and gas. They dispersed microscopic droplets of nickel-rich sulfides that traveled thousands of miles through the atmosphere. When these nickel aerosols settled in oceans and soils around the world, they provided a crucial nutrient for methane-producing archaea, ancient microorganisms that generate methane as a waste product. Suddenly supplied with abundant nickel, these microbes exploded in population and began pumping massive amounts of methane into the atmosphere. Methane is an extremely potent greenhouse gas, roughly 25 times more effective at trapping heat than carbon dioxide. The nickel-fed archaea essentially created a biological methane bomb that amplified the volcanic warming by orders of magnitude. This represents one of the most complex and devastating environmental disasters in Earth's history, a chain reaction that linked volcanism, atmospheric chemistry, and biological processes in a feedback loop of destruction. 42. Plants died first. Plants died 400,000 years before marine animals during the Great Dying, revealing the complex timeline of this massive extinction event. This discovery overturned previous assumptions about how the extinction unfolded. Scientists originally thought that marine and terrestrial ecosystems collapsed simultaneously, but evidence from Australian rock formations tells a different story. Terrestrial plant communities began dying hundreds of thousands of years before the main marine extinction, suggesting that the crisis built up gradually before reaching its devastating climax. The plant die-offs created a cascade of ecological collapse on land. Without vegetation to support them, terrestrial animal communities began fragmenting and declining long before the main extinction pulse. Soil erosion increased dramatically as root systems died, while the loss of plant cover altered local climate patterns and water cycles. This extended timeline suggests that the Great Dying wasn't a single catastrophic event, but rather a prolonged environmental crisis that built momentum over hundreds of thousands of years. By the time marine ecosystems began their final collapse, terrestrial environments had already been devastated, leaving Earth's biosphere critically weakened and vulnerable to the final devastating blow. 43. The mushroom takeover. The Permian extinction created a fungal spike in rocks worldwide as forests died and decomposer fungi exploded to feed on the epic meal of dead vegetation. As terrestrial ecosystems collapsed, fungi inherited the Earth in a way they never had before or since. With massive amounts of dead plant material suddenly available and few surviving organisms to compete with, fungal populations exploded across the globe. They essentially had a planetary buffet of decomposing organic matter all to themselves. This fungal boom was so pronounced that it left a clear signature in the geological record, a layer of rock enriched with fungal spores and organic compounds that could be detected worldwide. It's like a fossil record of decomposition, preserving evidence of the massive cleanup operation that fungi performed after the extinction. The fungal spike also reveals how ecosystems can completely reorganize during environmental crises. For a brief period in Earth's history, fungi became the dominant form of complex life, processing the remains of entire forest systems and recycling nutrients for whatever organisms would eventually inherit the post-extinction world. It was evolution's cleanup crew working overtime on a planetary scale. 44. The Boeing 737 of dinosaurs. Patagotitan majorum reached 120 feet in length and weighed over 70 tons, earning the nickname Boeing 737 of dinosaurs because its reconstructed skeleton doesn't fit entirely in most museum exhibition rooms. Standing next to a Patagotitan skeleton is like standing next to a commercial airliner. The creature was so massive that museums struggle to display complete specimens. The tail might extend into one room while the head reaches into another. A single vertebra from its neck is larger than a human torso, while its leg bones are taller than most people. The engineering challenges of being this large are almost incomprehensible. The animal's heart had to pump blood up a neck that extended 3 stories high, requiring blood pressure that would burst the blood vessels of smaller animals. The digestive system had to process literally tons of plant material daily, while the skeletal system had to support weight equivalent to 12 elephants. Yet Patagotitan wasn't just large, It was elegantly designed for its massive size. The bones were honeycombed with air spaces to reduce weight without sacrificing strength, while the body plan distributed mass efficiently to minimize stress on individual bones and joints. It represents the absolute pinnacle of dinosaur gigantism, the largest land animal that ever walked the earth. 45. The ultimate growth story. Argentinosaurus underwent the most extreme size transformation in animal history, growing from a 1 meter, 5 kilogram hatchling to a 65 to 110 ton adult, a 5 order of magnitude increase achieved in just 30 years. This growth rate represents one of the most remarkable biological achievements ever documented. To understand the scale, imagine a human baby growing to weigh 22,000 tons by age 30. That's equivalent to 200 blue whales. The dinosaur literally increased its body mass by a factor of 10 to 20 million times during its lifetime. The metabolic demands of this growth were staggering. Young Argentinosaurus had to consume massive amounts of food while simultaneously building the structural frameworks needed to support their ever-increasing size. They essentially had to redesign their entire body plan multiple times during growth, strengthening bones, enlarging organs, and reconfiguring their cardiovascular system. This rapid growth required perfect coordination between genetics, nutrition, and environmental conditions. Any disruption to food supply, disease, or injury during the critical growth phase could have been fatal. The fact that some individuals successfully completed this transformation represents one of evolution's greatest engineering achievements, growing a house-sized animal from a dog-sized baby in just 3 decades. 46. The first colored dinosaur. Sinosauropteryx became the first dinosaur with scientifically determined colors when researchers analyzed 125-million-year-old fossilized melanosums to reveal red-orange and white striped tail patterns. For over 150 years, paleontologists could only guess at dinosaur colors, typically imagining them in drab browns and greens like modern large animals. Then a revolutionary discovery changed everything. Scientists found that tiny structures called melanosomes, which contain color pigments, could survive fossilization and be analyzed under electron microscopes. The breakthrough came when researchers examined Sinosauropteryx feathers and discovered intact melanosomes that still contained their original pigments after 125 million years. By comparing these ancient structures to melanosomes in modern bird feathers, they could determine the exact colors and patterns that decorated this small Chinese dinosaur. The results were stunning. Instead of drab reptilian colors, Sinosauropteryx sported a vibrant red-orange coat with distinctive white stripes running along its tail. This discovery opened an entirely new field of paleontology, allowing scientists to study not just dinosaur anatomy and behavior, but their actual appearance and how they might have used color for display, camouflage, or communication. 47. The rainbow dinosaur. Kaihongjuji, literally meaning rainbow with a big crest, had iridescent feathers on its neck and chest that shimmered like modern hummingbird plumage. This wasn't just colored plumage. It was sophisticated optical engineering that created rainbow effects through microscopic feather structures. The dinosaur's neck and chest feathers contained platelet-shaped melanosomes arranged in precise layers that interfered with light waves to produce brilliant iridescent displays. The discovery of iridescence in dinosaurs reveals that these ancient animals were using some of the most advanced color-producing mechanisms known to biology. Iridescent feathers require incredibly precise, microscopic architecture. Tiny structures arranged in perfect geometric patterns that can manipulate light at the wavelength level. Kaihong likely used its rainbow display for courtship and social signaling, much like modern hummingbirds and peacocks. The ability to produce such sophisticated optical effects suggests that dinosaur behavior was far more complex and visually oriented than previously imagined. These weren't just large, lumbering reptiles. They were sophisticated animals capable of producing some of nature's most beautiful visual displays. 48. The feathered giant. Yutyrannus huali was a 30-foot, long-feathered giant closely related to T. rex, completely covered in downy feathers for insulation in cooler Cretaceous climates. The discovery of Yutyrannus shattered the image of massive theropod dinosaurs as scaly, reptilian monsters. Instead, this enormous predator resembled a giant, feathered bird with massive jaws and powerful claws. The feathers weren't for flight. They were sophisticated insulation that allowed the dinosaur to maintain stable body temperature in the cooler climates of Cretaceous China. At 30 feet long and weighing nearly 3,000 pounds, Yutyrannus was larger than most modern elephants, but covered in a coat of downy feathers like a massive, predatory chick. The feathers were simple, filamentous structures that trapped air for insulation, similar to down feathers in modern birds, but on an enormous scale. This discovery suggests that many large theropod dinosaurs may have been feathered, completely changing our mental image of these prehistoric predators. Instead of cold-blooded, scaly lizards, they were likely warm-blooded, feathered animals that were more bird-like than reptilian in their physiology and appearance. 49. The Cannibal King. Majungasaurus became the first confirmed cannibal dinosaur when scientists discovered bite marks on fossil bones that matched only its own distinctive teeth. The evidence for dinosaur cannibalism is written in stone, literally. Majungasaurus bones show clear bite marks with distinctive spacing and serration patterns that match only other Majungasaurus teeth. The bites weren't accidental scavenging. They showed evidence of active predation, with large chunks of bone bitten off and consumed. This discovery revealed a darker side of dinosaur behavior that paleontologists had long suspected but never proven. Cannibalism in large predators usually occurs during times of environmental stress, when normal prey becomes scarce and desperation drives individuals to hunt their own species. The bite marks on Majungasaurus bones show that these encounters were violent and often fatal. Some specimens preserve multiple bite marks from different feeding events, suggesting that injured or dead Majungasaurus regularly became meals for their own kind. This behavior provides insight into both the ecological pressures of late Cretaceous Madagascar and the opportunistic nature of large theropod predators. 50. Dinosaur cuddle puddles. 3 young oviraptorosaurs were discovered fossilized while huddling together for warmth, providing the first evidence of social roosting behavior in dinosaurs. This remarkable fossil captures an intimate moment from 67 million years ago. 3 juvenile dinosaurs, each about the size of a large turkey, died while sleeping together in a communal huddle. The positioning of their bodies shows they were deliberately seeking contact with each other, similar to how modern birds and mammals huddle for warmth and comfort. The discovery provides powerful evidence that dinosaurs weren't just social during mating or feeding, but maintained complex social bonds that included comfort behaviors. The young oviraptorosaurs show evidence of mutual grooming and positioning that suggests they actively cared for each other's well-being. This behavior implies sophisticated social intelligence in dinosaurs, the ability to recognize other individuals, form emotional bonds, and engage in altruistic behaviors that benefited group survival. It's a touching reminder that these ancient animals weren't just biological machines, but creatures capable of forming relationships and providing mutual care and comfort. 51. When mammals fought back. A 125-million-year-old fossil discovered in China shows a badger-sized mammal actively attacking a dog-sized dinosaur, completely overturning the idea that mammals were merely tiny, cowering creatures during the age of reptiles. The fossil preserves the moment of conflict in extraordinary detail. The mammal Reponomimus has its teeth embedded in the ribs of the small dinosaur Psittacosaurus, while its claws are positioned to grip the dinosaur's body. This wasn't scavenging of an already dead dinosaur. The positioning shows an active predator-prey encounter where the mammal was the aggressor. This discovery shattered the traditional narrative of Mesozoic ecosystems where mammals were portrayed as tiny, shrew-like creatures that lived in the shadows of giant reptiles. Instead, it reveals that some mammals were bold, capable predators willing to take on dinosaurs in direct combat. The fossil also demonstrates that ecological relationships in dinosaur-era ecosystems were far more complex than previously imagined. Rather than simple predator-prey hierarchies dominated by large reptiles, these ancient environments featured intricate webs of interactions where size didn't always determine who was hunter and who was prey. 52. The fighter jet of the skies. Quetzalcoatlus possessed a wingspan of 35 to 40 feet, equivalent to an F-16 fighter jet, making it the largest flying animal ever to grace Earth's skies. Picture a creature with wings that could span 4 lanes of highway, soaring over Cretaceous landscapes with the grace of a glider and the presence of a small aircraft. Quetzalcoatlus wasn't just large. It was engineered for flight with hollow bones, efficient wing membranes, and a skeletal structure that maximized wingspan while minimizing weight. The pterosaur's launch mechanism was equally impressive. Like modern vampire bats, Quetzalcoatlus used all 4 limbs to vault into the air, generating enough initial lift to become airborne despite weighing as much as a small car. Once aloft, it could soar for hours using thermal updrafts, covering vast distances with minimal energy expenditure. The creature's head alone was longer than most modern birds' entire bodies, featuring a massive beak perfectly adapted for its feeding strategy. Whether it was a fish eater, carrion feeder, or active predator, Quetzalcoatlus dominated Cretaceous skies with an authority that no flying animal has matched since its extinction 66 million years ago. 53. The four-winged pioneer. Microraptor revolutionized our understanding of dinosaur flight with its unique four-winged design, featuring flight feathers on both front and rear legs that enabled sophisticated gliding between trees. This small dinosaur represents a crucial link in understanding how dinosaurs evolved the ability to fly. Unlike modern birds, which use only their arms for flight, Microraptor had developed flight surfaces on all 4 limbs, creating a unique tetrapteryx body plan that has no modern equivalent. The rear leg wings weren't just simple extensions. They were sophisticated flight surfaces with asymmetrical feathers arranged in proper aerodynamic configurations. Computer models show that this four-wing design was highly efficient for gliding, allowing Microraptor to travel significant distances between trees while maintaining excellent maneuverability. This discovery suggests that early dinosaur flight may have evolved through a four-winged intermediate stage before eventually transitioning to the two-winged design of modern birds. Microraptor provides a glimpse into evolutionary experimentation, showing how nature tested different solutions to the challenge of powered flight before settling on the design that would eventually dominate the skies. 54. The whale of the Mesozoic. Mosasaurus reached lengths of 60 feet and maintained warm-blooded metabolism with body temperatures of 95 to 102 degrees Fahrenheit, essentially functioning as the Mesozoic equivalent of modern whales. These massive marine reptiles weren't just large lizards that happened to live in water. They were sophisticated marine predators with advanced physiological adaptations that paralleled those of modern whales. The ability to maintain warm body temperatures in cold ocean water required complex circulatory systems and high metabolic rates that challenged traditional ideas about reptilian physiology. Mosasaurus gave birth to live young in the ocean, just like modern whales and dolphins. Fossil evidence shows that baby mosasaurs were born tail-first underwater, suggesting that these ancient reptiles had evolved sophisticated birthing behaviors to prevent newborns from drowning during delivery. Some species of mosasaurs even invaded freshwater environments, with fossils found in ancient river systems far from marine environments. This ecological flexibility, combined with their warm-blooded physiology and live birth reproduction, made mosasaurs one of the most successful marine predator groups in Earth's history, dominating ocean ecosystems for over 30 million years. 55. The forgotten giant fish. Leedsichthys stretched over 50 feet in length, making it larger than most modern whales despite being a bony fish rather than a marine mammal. This massive fish challenges our assumptions about aquatic gigantism and the limits of fish size. While modern whale sharks can reach similar lengths, they are cartilaginous fish with lightweight skeletons. Leadsichthys achieved comparable size while maintaining a heavy, bony skeleton, an engineering challenge that required sophisticated anatomical adaptations. The discovery of Leadsichthys fossils initially confused paleontologists, who couldn't believe that a bony fish could grow to such enormous proportions. The creature lived alongside marine reptiles like plesiosaurs and mosasaurs, but achieved its size through completely different evolutionary strategies. Like modern whale sharks, Leadsichthys was likely a filter feeder that consumed massive quantities of plankton and small fish. Its enormous gill rakers would have strained food from the water as it swam with its mouth open, processing thousands of gallons of seawater to extract sufficient nutrition to fuel its massive body. 56. The greenhouse planet. During the Cretaceous period, global average temperatures soared 6 to 8 degrees Celsius warmer than today, while atmospheric CO2 levels exceeded 1,000 parts per million, creating a greenhouse world unlike anything in human experience. To understand this alien climate, imagine a world where winter simply doesn't exist. Even the polar regions enjoyed temperatures warmer than modern temperate zones, while tropical areas experience heat that would be lethal to most current life forms. The atmospheric CO2 concentration was nearly 4 times higher than pre-industrial levels, creating a runaway greenhouse effect that turned Earth into a global hothouse. This wasn't gradual warming. It was a complete transformation of planetary climate systems. Weather patterns that had existed for millions of years completely reorganized as temperature gradients between poles and equator nearly disappeared. Storm systems became more intense, but followed completely different paths, while precipitation patterns shifted dramatically across the globe. The Cretaceous greenhouse demonstrates how dramatically Earth's climate can change when atmospheric chemistry reaches tipping points. It serves as both a window into Earth's climatic extremes and a warning about how quickly planetary systems can reorganize when greenhouse gas concentrations exceed critical thresholds. 57. Arctic beaches. Ocean temperatures reached a staggering 95 degrees Fahrenheit at the poles during the Cretaceous, with absolutely no ice anywhere on Earth, creating tropical beach conditions in what are now the Arctic and Antarctic. Imagine palm-fringed beaches where the North Pole sits today, with water temperatures warm enough for swimming and marine life more diverse than modern tropical reefs. The Arctic Ocean was essentially a warm, shallow sea teeming with marine reptiles, tropical fish, and coral-like organisms that had never experienced freezing temperatures. This polar warming was so extreme that temperature differences between equator and poles were minimal, perhaps only 10 to 15 degrees Celsius compared to today's 40 to 50 degrees Celsius gradient. Without polar ice caps to drive global circulation patterns, ocean currents and atmospheric systems operated in completely alien ways that we can barely understand today. The absence of ice caps had profound effects beyond just temperature. Sea levels were dramatically higher, while the lack of seasonal ice formation meant that polar regions experienced continuous warmth year-round. Marine ecosystems extended to the very poles, creating global tropical conditions that supported life forms in regions now permanently frozen. 58. The drowned continents. Sea levels during the Cretaceous stood 500-plus feet higher than today, creating vast inland seas that split continents and fundamentally reorganized global geography. Picture North America split in half by a massive seaway that stretched from the Gulf of Mexico to the Arctic Ocean, with waves lapping its shores in what are now Kansas and Colorado. The Western Interior Seaway was essentially an inland ocean that divided the continent into eastern and western landmasses, each supporting completely different ecosystems. This wasn't just flooding of coastal areas. It was the complete submersion of vast continental regions under hundreds of feet of seawater. Mountain ranges that are now far inland were coastal ranges lapped by ocean waves, while entire river systems disappeared under marine environments. The high sea levels created island continents and archipelagos where solid land masses exist today. Marine life could swim over areas that are now major cities, while land animals were forced into isolated populations on scattered islands. This geographic fragmentation drove rapid evolution and speciation as populations became isolated on island continents, separated by hundreds of miles of open ocean. 59. Palm trees in Alaska. During the Cretaceous greenhouse world, palm trees and other tropical vegetation thrived in Alaska, supporting ecosystems from pole to pole that have no modern equivalent. The forests of Cretaceous Alaska were more like modern Amazon rainforests than anything resembling today's boreal ecosystems. Massive palm trees, ferns, and flowering plants created lush tropical canopies in regions that now experience months of winter darkness and sub-zero temperatures. These polar forests supported dinosaur populations that migrated seasonally or year-round, depending on the species. Hadrosaurs, tyrannosaurs, and ceratopsians roamed through steamy jungles where polar bears and caribou now struggle to survive. The contrast couldn't be more dramatic. Predators the size of school buses hunting through tropical vegetation in locations now dominated by ice and tundra. The existence of tropical vegetation at the poles also reveals how dramatically different day-night cycles affected these ecosystems. Despite warm temperatures, polar regions still experienced months of continuous daylight followed by months of darkness, creating unique growing conditions that have never been repeated in Earth's more recent history. 60. The ultimate impact. The Chicxulub asteroid impact released energy equivalent to 100 million megatons of TNT, a billion times more powerful than the atomic bombs that ended World War II. To comprehend this scale of destruction, imagine the explosive force of every nuclear weapon ever built detonating simultaneously, then multiply that by several thousand. The asteroid, roughly 6 miles in diameter, was traveling at 45,000 miles per hour when it struck the Yucatan Peninsula, delivering kinetic energy that defies human understanding. The impact occurred in shallow tropical seas, which made the devastation even worse. The asteroid vaporized thousands of cubic miles of water instantly, creating a steam explosion that dwarfed any volcanic eruption in recorded history. The water didn't just boil, it was converted directly from liquid to superheated vapor in a fraction of a second. The energy release was so enormous that it briefly created temperatures approaching those found in the core of the sun. Rock, water, and asteroid material were not just melted, but vaporized and launched into space, creating a temporary ring of debris around Earth while raining molten glass spherules across the entire planet. 61. Global destruction in minutes. The Chicxulub impact created a magnitude 101 earthquake, generated 300-foot tsunamis, and briefly blocked out the sun globally through atmospheric debris. The earthquake was unlike anything in recorded history, a magnitude 101 quake that would have been felt on the opposite side of the planet with devastating intensity. For comparison, the largest earthquake ever measured was magnitude 95, and each unit on the Richter scale represents a 10-fold increase in energy. The impact earthquake was roughly 40 times more powerful than the strongest quake in human history. The tsunamis generated by the impact dwarfed any natural disaster in human experience. Waves over 300 feet tall, the height of 30-story buildings, raced across ocean basins at jet aircraft speeds, devastating coastal regions thousands of miles from the impact site. These weren't just large waves, they were moving walls of water that could overtop mountain ranges. Perhaps most catastrophically, the impact threw so much debris into the atmosphere that it created a global winter lasting months or years. Dust, ash, and vaporized rock blocked out the sun completely, halting photosynthesis worldwide and collapsing food webs from the bottom up. 62. The ultimate land giant. Parasauritherium stood 17 feet tall at the shoulder and weighed 15 to 33 tons, equivalent to 5 modern elephants, while browsing vegetation 25-plus feet off the ground with its giraffe-like neck. Picture a rhinoceros scaled up to the size of a house, with legs like tree trunks and a neck long enough to browse treetops. Paraceratherium represents the absolute peak of land mammal size, pushing the physical limits of what's possible for a terrestrial animal. Standing next to this creature would be like standing next to a two-story building that could walk. The engineering challenges of supporting such massive size on land were enormous. The creature's leg bones were thicker than telephone poles, while its spine had to distribute weight across a framework that could support loads equivalent to several large trucks. Despite its massive size, Paraceratherium was built for mobility, capable of traveling long distances in search of the enormous quantities of vegetation needed to fuel its metabolism. The long neck allowed Paraceratherium to exploit food sources unavailable to other mammals, browsing from tree canopies like a massive, hornless giraffe. This ecological niche, large mammalian high browser, has never been filled again since Paraceratherium's extinction, leaving modern ecosystems without any equivalent to this gentle giant. 63. The wolf that ate horses. Andrewsarchus was a 1-ton predatory mammal measuring 13 feet in length, making it the largest terrestrial carnivorous mammal ever discovered, essentially a wolf scaled up to horse-killing size. Imagine a wolf with the body mass of a small car and jaws powerful enough to crush the bones of animals the size of modern horses. Andrewsarchus represents the pinnacle of mammalian predatory evolution, combining the hunting instincts of modern wolves with the size and power needed to take down megafauna prey. The creature's skull alone was over 3 feet long, housing jaws filled with teeth designed for both slicing meat and crushing bones. This combination of cutting and crushing dental equipment suggests that Andrewsarchus was both an active hunter and a bone-cracking scavenger, capable of extracting every possible nutrient from its massive prey. Living in the Eocene epoch when large mammals were diversifying rapidly, Andrewsarchus likely preyed on early horses, primitive rhinoceros relatives, and other large herbivores. Its size and power would have made it the apex predator of its ecosystem, capable of taking down prey that no modern terrestrial carnivore could handle. 64. The racing bear. Arctidus emus, the short-faced bear, stood 10 feet tall on its hind legs and weighed up to 1,749 pounds, while maintaining the ability to run 40 miles per hour despite its massive size. Picture a bear larger than a polar bear that could outrun a racehorse. Arctidus combined impossible size with remarkable speed, creating a predator that was both overwhelmingly powerful and surprisingly fast. Standing on its hind legs, it was tall enough to look into second-story windows, while its running speed was faster than any human could achieve, even with modern training. The bear's long legs and lean build were optimized for speed rather than the lumbering gait typical of modern bears. This suggests that Arctidus was an active pursuit predator rather than the opportunistic forager that characterizes most bear species. It likely ran down prey across open landscapes, using its size advantage to overpower victims after high-speed chases. Recent research indicates that Arctidus was highly carnivorous, more like a giant wolf than a typical omnivorous bear. Its specialized hunting lifestyle and massive size made it one of North America's most formidable predators until its extinction roughly 11,000 years ago, possibly due to competition with humans and climate change. 65. The bust-sized sloth. Megatherium reached 20 feet in length and weighed 9,000 pounds, making it a bust-sized ground sloth with 3-foot-long claws that survived until just 10,000 years ago. Imagine a sloth the size of a city bus, with claws longer than baseball bats and the ability to rear up 12 feet high to browse from tree canopies. Megatherium represents one of evolution's most successful experiments in extreme size, creating a herbivore so massive that it had virtually no natural predators. The creature's enormous claws weren't weapons. They were sophisticated tools for manipulating vegetation. Megatherium could grasp entire tree branches and strip them of leaves, or dig massive burrows for shelter. Some paleontologists suggest these giants could even knock down entire trees to access fresh foliage in the canopy. What makes Megatherium particularly remarkable is how recently it existed. These giants were still alive when humans first entered South America, and cave paintings may even depict encounters between early people and these massive sloths. Their extinction roughly 10,000 years ago marks the end of an era when truly giant mammals still roamed the Earth. 66. The instant climate crisis. The Paleocene thermal maximum saw global temperatures spike by 9 degrees Fahrenheit in just a few thousand years 56 million years ago, representing one of the most rapid climate changes in Earth's history. This ancient climate crisis occurred at a speed that makes modern climate change seem gradual by comparison. In just 3,000 to 4,000 years, barely an instant in geological time, global temperatures rose by nearly 10 degrees Fahrenheit, creating environmental chaos that reshaped ecosystems worldwide. The temperature spike was triggered by massive carbon release, possibly from volcanic activity or the sudden breakdown of methane hydrates on ocean floors. Whatever the cause, it pumped greenhouse gases into the atmosphere faster than natural processes could absorb them, creating a runaway warming effect. The environmental consequences were dramatic and global. Tropical conditions extended to the Arctic Circle, while desert regions experienced unprecedented heat that made them virtually uninhabitable. Ocean circulation patterns completely reorganized, creating new weather systems and precipitation patterns that persisted for hundreds of thousands of years. This ancient crisis provides a sobering preview of how quickly planetary climate systems can reorganize when greenhouse gas concentrations reach critical thresholds. 67. Arctic tropics. During the PTM, Arctic Ocean temperatures reached 73 degrees Fahrenheit, equivalent to modern subtropical seas and warmer than many current vacation destinations. Picture the North Pole as a warm, inviting swimming destination with water temperatures comfortable enough for tropical marine life. Palm trees lined Arctic shores while coral reefs grew in waters that now remain frozen for most of the year. The Arctic Ocean was essentially a giant warm bathtub, supporting ecosystems more diverse than modern Caribbean reefs. This extreme Arctic warming eliminated all polar ice and created weather patterns unlike anything in modern experience. Without cold polar air masses to drive global circulation, atmospheric systems operated in completely alien ways. Storm tracks, precipitation patterns, and seasonal cycles were fundamentally different from anything humans have ever experienced. The warm Arctic also supported land-based tropical ecosystems extending to the very poles. Rainforests with palm trees, tropical ferns, and exotic flowering plants thrived where polar bears and walruses now struggle to survive. Early primates, crocodilians, and other warm climate animals lived in regions now characterized by permafrost and tundra vegetation. 68. India's volcanic rage. The Deccan Traps volcanic eruptions released enough lava to cover France in layers 2 kilometers thick, while causing 78 degrees Celsius of global warming that may have contributed more to dinosaur extinction than the asteroid impact. Picture volcanic eruptions so massive they could bury an entire European country under lava flows over a mile deep. The Deccan Traps weren't ordinary volcanoes. They were massive outpourings of flood basalt that continued for hundreds of thousands of years, releasing volumes of lava that dwarf any volcanic activity in recorded human history. The environmental impact extended far beyond the immediate lava flows. The eruptions released massive amounts of sulfur dioxide and carbon dioxide that poisoned the atmosphere and triggered severe global warming. The 78 degrees Celsius temperature increase was equivalent to turning Earth into a planetary oven, creating conditions that made survival difficult for large animals. Recent research suggests that the Deccan eruptions may have weakened dinosaur ecosystems for hundreds of thousands of years before the asteroid delivered the final blow. Rather than a single catastrophic impact, dinosaur extinction may have resulted from a 1-2 punch of volcanic climate change, followed by asteroid devastation, a double catastrophe that overwhelmed even the most adaptable species. 69. The Yellowstone Monster. Yellowstone's supervolcano has erupted 3 times in the past 21 million years, each releasing over 1,000 cubic kilometers of material and burying much of North America in volcanic ash several feet deep. Each Yellowstone supereruption was roughly 1,000 times more powerful than the 1980 Mount St. Helens eruption, creating ash clouds that reached the stratosphere and circled the globe multiple times. The most recent eruption, 640,000 years ago, ejected enough material to bury the entire state of Texas under 3 feet of volcanic debris. The ash falls from these eruptions extended across the entire continent, with measurable deposits found as far away as the Atlantic coast. Animals unfortunate enough to be downwind of the eruptions faced death by suffocation, while plant communities were buried under ash layers that took decades to weather into soil. Perhaps most concerning, the Yellowstone caldera shows signs of ongoing activity. The ground has risen 25 centimeters since 2004, indicating magma accumulation beneath the surface. While another supereruption isn't predicted in the near future, the volcanic system remains active and continues to pose one of the most significant natural hazards on the North American continent. 70. Rising ground. The ground at Yellowstone has risen 25 centimeters since 2004, indicating ongoing magma accumulation beneath one of the world's most dangerous volcanic systems. This ground deformation represents the breathing of a sleeping giant. As magma accumulates in the massive chamber beneath Yellowstone, it pushes upward against the overlying rock, causing measurable surface elevation changes that can be detected by satellite imagery and ground-based monitoring systems. The rate of ground rise varies over time, sometimes accelerating to several centimeters per year during periods of increased magma injection, then slowing or even reversing as the underground system reorganizes. This dynamic behavior provides scientists with real-time insight into the processes occurring miles beneath the surface. While ground deformation doesn't necessarily indicate an imminent eruption, it confirms that the Yellowstone system remains very much alive. The magma chamber is actively growing and evolving, fed by deep mantle processes that have operated for millions of years. This ongoing activity serves as a reminder that supervolcanoes operate on timescales far longer than human civilization, but their potential impact on modern society would be unprecedented. 71. Living in an ice age. We are currently living in an ice age that began 34 million years ago, the late Cenozoic Ice Age, with permanent ice caps representing abnormal conditions in Earth's long-term climate history. Most people don't realize that Earth's current climate, with permanent ice at both poles, represents one of the most unusual climate states in our planet's history. For most of the past 500 million years, Earth was completely ice-free, with tropical or temperate conditions extending to the poles. The presence of permanent ice caps is actually the exception, not the rule. The late Cenozoic Ice Age began when Antarctica first became covered in ice 34 million years ago, followed by the growth of Arctic ice caps much more recently. This cooling trend culminated in the Pleistocene ice ages, when massive ice sheets periodically covered much of North America and Northern Europe. We're currently living in an interglacial period, a brief warm interval between glacial advances. Based on natural cycles, the next glacial period should begin within the next few thousand years, though human-induced climate change may be postponing or preventing this natural progression. Understanding our current position within a longer ice age provides crucial context for evaluating both natural climate variability and human climate impacts. 72. Climate's wild swings. Global temperatures have swung 3 to 8 degrees Celsius every 100,000 years over the past million years, creating massive environmental changes that dwarf anything in recorded human history. These temperature swings represent complete reorganizations of global climate systems occurring with clockwork regularity. Every 100,000 years, Earth transitions from conditions similar to today into full glacial periods where ice sheets cover much of North America and Northern Europe, then rapidly returns to interglacial warmth. The speed of these transitions is particularly striking. While the cooling into glacial periods occurs gradually over tens of thousands of years, the warming back to interglacial conditions can happen in just a few thousand years, rapid enough to be observable within human lifespans if they occur today. These natural climate cycles are driven by subtle changes in Earth's orbital patterns, variations in the shape of Earth's orbit, the tilt of its axis, and the timing of seasons. These Milankovitch cycles create only minor changes in solar energy reaching Earth, but they trigger massive feedback effects involving ice sheets, ocean circulation, and atmospheric composition that amplify small orbital changes into dramatic climate swings. 73. The frozen world. Ice sheets covered 30% of Earth's land surface during the most recent glacial maximum 20,000 years ago, creating a world that would be barely recognizable to modern humans. Picture a world where glaciers over a mile thick covered all of Canada, the northern United States, and most of northern Europe. These weren't just snow accumulations, they were massive rivers of ice that flowed across continents, carving valleys, moving mountains, and completely reshaping the landscape. The ice sheets were so massive they actually depressed the Earth crust beneath them. When the glaciers melted, the land slowly rebounded upward, a process that continues today in places like Scandinavia and northern Canada, where the ground is still rising in response to the removal of Ice Age glacial load. The presence of so much ice locked up on land had profound effects on global climate and geography. Weather patterns were completely different, with massive dust storms, altered precipitation patterns, and atmospheric circulation systems that have no modern equivalent. Much of the planet that wasn't covered in ice was desert, as the global water cycle was disrupted by the presence of massive ice sheets. 74. The drained oceans. Sea levels dropped 400 feet during the last glacial maximum, exposing vast continental shelves and creating land bridges that connected continents. With so much water locked up in glacial ice, ocean basins were partially drained, exposing areas that are now hundreds of feet underwater. The Bering Land Bridge connected Asia and North America, allowing human migration to the Americas. Similarly, Britain was connected to continental Europe, while vast areas of the current ocean floor were dry land supporting terrestrial ecosystems. These exposed continental shelves weren't just barren mudflats. They supported forests, grasslands, and complete terrestrial ecosystems that are now completely submerged. Archaeological evidence suggests that some of the richest hunting grounds for Ice Age humans were in areas that are now under hundreds of feet of seawater. The geography of the Ice Age world was fundamentally different, with land connections allowing plant and animal migrations that are impossible today. When the ice sheets melted, rising sea levels not only flooded these exposed areas, but also buried entire ecosystems and human settlements beneath modern ocean waters. 75. The Great Dying of Giants. The end of the Pleistocene witnessed a catastrophic extinction that eliminated 88% of large mammals in Australia, 83% in South America, and 72% in North America, a size-biased massacre that preferentially targeted the biggest animals. This wasn't a random extinction. It was a systematic elimination of large animals that follows a clear pattern worldwide. The larger the animal, the more likely it was to go extinct. Mammoths, giant ground sloths, saber-toothed cats, and massive bears all disappeared, while smaller animals like rodents, bats, and small birds largely survived. The pattern is so consistent across different continents and environments that it points to a common cause rather than local environmental changes. The timing also correlates closely with human expansion into new continents, suggesting the human hunting pressure was the primary driver of these extinctions. What makes this extinction particularly tragic is that it eliminated entire ecological guilds, groups of animals that performed similar functions in ecosystems. The loss of large herbivores, for example, meant that many plant communities lost their primary seed dispersers and ecosystem engineers, leading to cascading ecological changes that persist today. 76. The 2,000-Year Massacre. In North America, 32 genera of large mammals disappeared in just 2,000 years around 11,000 years ago, representing one of the most rapid extinction events in mammalian history. This time frame represents an ecological instant, faster than most species can adapt to environmental changes. The rapidity of the extinctions rules out gradual climate change as the primary cause and points instead to a sudden, overwhelming pressure that large mammals couldn't survive. Archaeological evidence provides smoking gun proof of human involvement. Specialized hunting tools designed specifically for killing mammoth-sized prey appear in the archaeological record at exactly the same time as the extinctions. Clovis points and other megafauna hunting technologies are found in direct association with kill sites containing the remains of extinct giant animals. The extinction followed a clear geographic pattern, moving from Alaska through North America as human populations expanded southward. Each region experienced massive mammal extinctions within centuries of first human arrival, creating a wave of destruction that swept across the continent faster than the animals could adapt or migrate to safer areas. 77. The Smoking Gun. Archaeological evidence reveals specialized hunting tools designed specifically for killing mammoth-sized prey, providing direct proof that humans caused the megafauna extinctions through targeted hunting. These weren't general-purpose tools adapted for hunting large animals. They were sophisticated weapons engineered specifically for taking down megafauna. Clovis points, atlatl darts, and specialized spear throwers show evidence of design optimization for penetrating thick hides and delivering killing blows to animals weighing several tons. The hunting technology was remarkably effective and appears to have spread rapidly across human populations. Radiocarbon dating shows that these specialized megafauna hunting cultures appeared suddenly and coincided exactly with extinction events. Within a few centuries of developing effective large animal hunting techniques, human groups had eliminated most giant mammals from entire continents. The archaeological record also preserves evidence of hunting behavior that goes beyond subsistence needs. Some kill sites contain far more meat than could be consumed by the hunting groups, suggesting that early humans were capable of overhunting, killing more animals than necessary for survival, and contributing to population crashes in prey species. 78. The Lonely Survivors. Only 11 out of 57 species of megaherbivores over 1,000 kilograms survive to the present day, creating modern ecosystems that are impoverished compared to their Ice Age predecessors. Today's largest land animals, elephants, rhinoceros, hippos, and a few others, represent the scattered survivors of a much richer community of giants. During the Pleistocene, every continent except Antarctica supported diverse communities of massive herbivores that filled ecological roles now left vacant. The loss of these giants had cascading effects that continue to shape modern ecosystems. Many plant communities evolved in partnership with large herbivores and still show adaptations for animals that no longer exist. Fruits too large for any surviving animal to disperse, defensive structures designed to deter extinct browsers, and seed dispersal mechanisms optimized for giant guts all persist as evolutionary echoes of the vanished megafauna. Modern conservation efforts are essentially trying to protect the last remnants of Ice Age biodiversity. The elephants, rhinos, and other giants that we work so hard to save represent evolutionary lineages that once included dozens of species, but now hang on by a thread, survivors of humanity's first global environmental impact. 79. Broken ecosystems. Ecosystems worldwide are still disrupted by the loss of Pleistocene megafauna, as large mammals were essential for seed dispersal, forest management, and nutrient cycling across continents. The ecological roles filled by extinct megafauna have largely remained vacant for the past 10,000 years, creating ecosystems that are fundamentally broken compared to their Ice Age predecessors. Large herbivores weren't just consumers. They were ecosystem engineers that maintained grasslands, dispersed nutrients, and created habitat heterogeneity through their feeding and movement patterns. Without large herbivores to browse vegetation and trample undergrowth, many grassland ecosystems have converted to forests or scrubland. This vegetation change affects everything from fire regimes to carbon storage, water cycles, and wildlife habitat. Some scientists estimate that rewilding efforts using proxy species for extinct megafauna could help restore ecosystem functions that have been missing for millennia. The nutrient cycling performed by large mammals was particularly important. Megafauna moved nutrients from productive areas where they fed to less fertile areas where they defecated, creating a biological pump that distributed fertility across landscapes. Without this service, many ecosystems have become nutrient-limited, supporting lower biodiversity and reduced productivity. 80. The mushroom connection. Humans are more closely related to mushrooms than mushrooms are to plants, with genetic analysis revealing that humans and fungi share about 50% of their DNA and belong to the same evolutionary supergroup. This shocking discovery completely overturns intuitive assumptions about the tree of life. While plants seem more similar to animals in their multicellular complexity, genetic analysis reveals that fungi and animals are actually sister groups that share a more recent common ancestor with each other than either shares with plants. The genetic similarities between humans and fungi are striking. Many fundamental cellular processes, protein structures, and metabolic pathways are more similar between animals and fungi than between fungi and plants. This explains why many antibiotics that kill bacteria are produced by fungi. They evolved biochemical weapons that are safe for animal-like cells but toxic to more distantly related organisms. This relationship has practical implications for medical research and biotechnology. Many human diseases can be studied using fungal model systems, while fungal enzymes and biochemical pathways often work directly in human cells. The evolutionary connection between animals and fungi represents one of the most significant discoveries in understanding the deep structure of life on Earth. 81. Evolution's crab obsession. The crab body plan has evolved independently at least 5 times in different crustacean lineages, a phenomenon so common it has its own scientific term: carcinization. Evolution seems to have an irresistible attraction to the crab form. Starting from completely different ancestral body plans, multiple groups of crustaceans have independently converged on the same basic design: a short, wide body with a reduced tail tucked under the main body section, and specialized appendages for feeding and defense. This repeated evolution of crab-like forms suggests that the crab body plan represents an optimal solution to certain environmental challenges. The design provides excellent protection for vital organs, efficient locomotion in complex three-dimensional environments, and versatile appendage arrangements that can be adapted for various feeding strategies. What makes carcinization particularly fascinating is that it's ongoing. Scientists can observe groups of crustaceans that are currently evolving toward crab-like forms. Some hermit crabs are losing their dependence on borrowed shells and developing their own protective carapaces, essentially becoming true crabs through evolutionary convergence. 82. Evolution in reverse. Evolution has also unmade crabs at least 7 times through decarcinization, showing that evolutionary trends can reverse when environmental pressures change. Perhaps even more remarkable than evolution's tendency to create crabs is its ability to uncreate them. Several lineages of true crabs have evolved back into more elongated, shrimp-like forms when their environments favored different body plans. This evolutionary reversal challenges simple notions of evolutionary progress or direction. Decarcinization typically occurs when crabs colonize environments where their compact body plan becomes disadvantageous. Some have evolved longer, more flexible bodies for burrowing, while others have developed streamlined forms for swimming. The process shows that evolution is remarkably flexible and can reverse even strongly established body plans when necessary. This back-and-forth evolution between crab and non-crab forms demonstrates that evolution doesn't have predetermined directions or goals. Instead, it's an ongoing process of optimization for current environmental conditions, capable of both moving toward and away from any particular body plan, depending on what works best for survival and reproduction. 83. The eye revolution. Eyes evolved independently 40 to 65 times across different animal groups, making vision one of evolution's most repeated inventions and demonstrating the incredible value of light detection for survival. The evolution of eyes represents one of the most dramatic examples of convergent evolution in biology. From the simple eye spots of jellyfish to the compound eyes of insects to the camera eyes of vertebrates, animals have invented vision systems using completely different developmental pathways and structural approaches. Each independent evolution of eyes solved the same basic problem: how to gather and process information from light, but used different solutions. Some animals evolved mirror-based eyes, others use lenses, still others rely on pinhole camera principles. The diversity of eye designs shows that there are many ways to achieve effective vision. What makes this repeated evolution particularly remarkable is the speed at which complex eyes can evolve. Computer simulations show that a sophisticated camera eye with lens, adjustable aperture, and high-resolution retina can evolve from a simple light-sensitive patch in fewer than 400,000 generations, an evolutionary instant for most animals. 84. Eyes and fast-forward. Computer models demonstrate that a complex camera eye can evolve from a simple light-sensitive patch in just 364,000 generations, showing that sophisticated vision can evolve surprisingly quickly. This computational discovery shattered the long-held belief that eyes were irreducibly complex structures that couldn't evolve gradually. By modeling the step-by-step evolution of eye components, scientists demonstrated that each intermediate stage provides survival advantages, creating a smooth evolutionary pathway from simple to complex vision. The modeling shows that even small improvements in vision provide significant survival advantages. Animals with slightly better light detection can find food more efficiently, avoid predators more effectively, and locate mates more successfully. These advantages accumulate over generations, driving rapid evolution toward increasingly sophisticated visual systems. The 364,000 generation time frame varies dramatically depending on generation time. For organisms that reproduce annually, this represents less than 400,000 years, a brief moment in evolutionary time. For organisms with shorter generation times, complex eyes could evolve in just tens of thousands of years, explaining why vision systems appear suddenly in the fossil record. 85. The electric revolution. Electric organs evolved independently 6 times in different fish lineages using completely different genetic pathways, yet achieving remarkably similar electrical capabilities. The independent evolution of bioelectricity in fish represents one of the most striking examples of convergent evolution in the animal kingdom. Electric eels, electric rays, electric catfish, and several other groups all developed the ability to generate powerful electrical discharges, but they did so using completely different cellular and genetic mechanisms. Despite using different developmental pathways, these electric organs achieve remarkably similar performance characteristics. They can generate voltages exceeding 600 volts and deliver current sufficient to stun large prey or deter predators. The electrical output is precisely controlled and can be modulated for different purposes: navigation, communication, hunting, or defense. Recent genetic analysis has revealed that while the organs themselves evolved independently, they often co-opted similar types of genes, particularly those involved in nerve and muscle function. This shows that while evolution found different solutions to the problem of bioelectricity, it repeatedly used similar molecular tools, suggesting there may be limited ways to achieve effective electrical generation in living tissue. 86. Underground evolution. London underground mosquitoes have evolved since 1863 and can no longer breed with surface mosquitoes, demonstrating rapid speciation in urban environments. The London Underground represents one of the most dramatic examples of rapid evolution in response to human-created environments. In less than 160 years, roughly 100 to 150 mosquito generations, the underground population has diverged so much from surface mosquitoes that they can no longer interbreed, meeting the biological definition of a separate species. The underground mosquitoes have adapted to a completely different lifestyle than their surface relatives. They don't hibernate during winter. They can breed without blood meals. They prefer different hosts, humans versus birds, and they show different mating behaviors. These changes represent a complete ecological shift packed into an extremely short evolutionary time frame. What makes this evolution particularly remarkable is that it occurred in isolation pockets within a major city. The mosquitoes colonized different underground lines independently and have evolved slightly different adaptations on each line, creating multiple evolutionary experiments within the same urban environment. This ongoing speciation provides scientists with a real-time view of how new species form. 87. Evolution in real time. Guppies in Trinidad evolved different life history traits in just 4 years when moved to new environments, showing that evolution can occur rapidly enough to observe directly. When researchers moved guppies from high predation streams to low predation streams, the fish began evolving within a single generation. Within 4 years, the transplanted populations showed significant changes in body size, reproduction timing, and behavior, evolutionary changes that occurred faster than most scientific studies. The guppies in low predation environments evolved larger body size, delayed reproduction, and reduced escape behaviors. These changes make sense evolutionarily. Without heavy predation pressure, the fish could invest more energy in growth and less in reproduction and escape responses. The speed of change demonstrates that evolution can respond to environmental shifts within human observable timeframes. This rapid evolution has been documented in many other organisms exposed to environmental changes. Urban animals, species introduced to new environments, and organisms facing climate change all show evidence of rapid evolutionary adaptation occurring over years or decades rather than millennia. 88. Dinosaur blood preserved. Scientists have recovered 68-million-year-old dinosaur proteins, blood vessels, and cellular structures from T. rex fossils, revolutionizing our understanding of biomolecule preservation and opening new avenues for studying ancient life. The discovery of preserved organic molecules in dinosaur fossils was initially met with skepticism from the scientific community. Conventional wisdom held that proteins and other complex biological molecules couldn't survive for more than a few thousand years, let alone tens of millions. Yet careful analysis using state-of-the-art techniques confirmed the presence of collagen proteins, blood vessel structures, and even cellular components in T. rex bones. These preserved biomolecules aren't complete, they're fragments and altered versions of the original molecules. But they retain enough of their original structure to provide insights into dinosaur physiology, growth rates, and evolutionary relationships. The proteins show that T. rex was more closely related to modern birds than to crocodiles, supporting the dinosaur-bird evolutionary connection. The preservation appears to result from iron-mediated cross-linking that creates extremely stable molecular structures. Iron from hemoglobin acts like a natural formaldehyde, creating chemical bonds that protect proteins from degradation over geological timescales. This discovery suggests that organic molecules might be preserved in many more fossils than previously thought. 89. The immortal protein. Dinosaur collagen's special molecular structure protects it from degradation for hundreds of millions of years through iron-mediated cross-linking that creates virtually indestructible protein networks. The preservation mechanism that protects dinosaur proteins reads like advanced materials science. When dinosaurs died, iron from their blood began forming chemical crosslinks between collagen molecules, creating a three-dimensional network of interconnected proteins that becomes increasingly stable over time. This iron-mediated preservation creates molecular structures so stable they can survive conditions that would destroy most organic compounds. The cross-linked collagen networks resist bacterial degradation, chemical breakdown, and physical disruption, essentially turning ancient proteins into biological plastics that can persist for geological ages. The discovery has implications beyond paleontology. Understanding how nature creates ultra-stable protein structures could lead to advances in materials science, medicine, and biotechnology. The iron cross-linking mechanism might be applicable to creating new biomaterials, preserving tissues for medical applications, or developing more durable biological products. 90. Amber's perfect prison. A 99-million-year-old dinosaur tail preserved in Myanmar amber shows three-dimensional feathers, soft tissue, and even traces of blood hemoglobin, providing an unprecedented window into dinosaur anatomy. The amber-preserved dinosaur tail represents one of the most extraordinary fossils ever discovered, capturing a moment in time with Hollywood movie perfection. Unlike typical fossils that preserve only bones and teeth, this amber specimen contains the actual soft tissues, complete with cellular detail that can be studied under powerful microscopes. The preservation is so perfect that individual feathers retain their three-dimensional structure, showing barbs, barbules, and color patterns that can be analyzed to determine the original appearance of the dinosaur. The feathers show a chestnut brown and white coloration pattern, revealing that this young Coelurosaur had distinctive striped plumage. Even more remarkably, the amber contains traces of hemoglobin, the iron-rich protein that carries oxygen in blood. This represents the first confirmed discovery of dinosaur blood proteins, providing direct evidence of dinosaur physiology and supporting theories about their warm-blooded metabolism. 91. The jeweler's fossil. The amber-preserved dinosaur tail was nearly sold as jewelry before its scientific significance was recognized, highlighting the ongoing threat to paleontological specimens from commercial fossil markets. This near-catastrophe illustrates a major problem in paleontology, scientifically invaluable specimens being lost to private collectors and jewelry makers who don't recognize their research value. The Myanmar amber markets are filled with specimens containing prehistoric insects, spiders, and plant material that could provide crucial insights into ancient ecosystems. The dinosaur tail specimen was rescued from the jewelry market by paleontologists who recognized its significance and purchased it before it could be carved into decorative objects. Many other specimens of equal scientific value have likely been lost forever, carved into pendants or decorative items that destroy their research potential. This incident has led to increased efforts to educate amber dealers about the scientific value of their specimens and establish partnerships that can preserve important finds while still providing economic benefits to local communities. However, the commercial amber trade continues to pose a significant threat to paleontological knowledge. 92. The small-brained genius. Homo naledi, with brains only one-third the size of modern humans, engaged in deliberate burial practices and symbolic engraving 335,000 to 236,000 years ago, challenging assumptions about the relationship between brain size and cognitive complexity. The discovery of Homo naledi burial practices revolutionized our understanding of human evolution and cognition. These ancient hominins had brains roughly the size of orangutans, about 450 to 550 cubic centimeters compared to the 1,400 cubic centimeters of modern humans. Yet they engaged in behaviors previously thought to require large, modern human-sized brains. The evidence for deliberate burial is compelling. Naledi remains are found in deep cave chambers that would have required difficult navigation to reach, with no evidence of predator activity or natural death. The bodies appear to have been deliberately placed in these locations, suggesting ritualistic or symbolic behavior that implies abstract thinking. Even more striking, Naledi appears to have created symbolic engravings on cave walls, geometric patterns that show intentional design and planning. These discoveries force scientists to reconsider the relationship between brain size and cognitive ability, suggesting that complex behaviors can emerge with much smaller neural networks than previously thought. 93. The Ancient Engineers. 476,000-year-old wooden structures, discovered in Zambia, represent the earliest known complex multi-part construction, predating Homo sapiens by 176,000 years and suggesting that earlier human species possessed sophisticated planning abilities. The Zambian wooden structures consist of carefully shaped logs joined together with precise notches and joints, demonstrating advanced planning, tool use, and engineering skills. The construction required multiple steps: selecting appropriate wood, shaping it with stone tools, creating precise joints, and assembling the components into stable structures. What makes this discovery particularly remarkable is its age, nearly 500,000 years old, created by human ancestors who had much smaller brains than modern humans. The structures predate Homo sapiens by almost 200,000 years, indicating that sophisticated construction abilities evolved much earlier than previously thought. The wooden structures also demonstrate that early humans were capable of planning complex, multi-step projects that required abstract thinking and future planning. The builders had to envision the final structure, gather appropriate materials, and execute a construction sequence, cognitive abilities that suggest much more advanced mental capabilities than typically attributed to early human species. 94. Earth's greatest volcanic catastrophe. The Siberian Traps erupted 720,000 cubic miles of lava over hundreds of thousands of years, releasing enough molten rock to bury the entire continental United States under 300 feet of basalt. To visualize this scale of volcanic activity, imagine the entire lower 48 United States covered in lava flows deep enough to submerge a 30-story building. The Siberian Traps represent the largest known volcanic event in Earth's history, dwarfing any eruption witnessed by humans by factors of thousands. The eruptions weren't explosive like Mount St. Helens or Krakatoa. They were massive outpourings of flood basalt that continued for up to 600,000 years. Fissures hundreds of miles long split open across Siberia, releasing rivers of lava that flowed for thousands of miles and accumulated in layers kilometers thick. The environmental impact was global and catastrophic. The eruptions released enough sulfur dioxide to create acid rain worldwide, while carbon dioxide and methane emissions triggered the most severe greenhouse warming in Earth's history. The combination of toxic gases, acid rain, and extreme warming created the conditions that drove the Permian Triassic extinction, the closest Earth has ever come to complete biological sterilization. 95. The Continental Collision. India crashed into Asia 50 million years ago while traveling at twice the speed of modern continental drift, creating the most dramatic geological collision in recent Earth history. Most continental drift occurs at speeds of 2 to 4 centimeters per year, roughly the rate at which fingernails grow. But India was moving at nearly twice this speed when it collided with Asia, driven by exceptionally strong mantle currents that pushed the subcontinent northward with unusual force. The collision was geologically catastrophic. India's leading edge crumpled and compressed as it pushed into the Asian continent, while the impact shortened the combined landmass by 900 to 1,500 kilometers. Rock layers that had formed at sea level were thrust upward to create mountain peaks over 8,000 meters high. The India-Asia collision wasn't a single event, but an ongoing process that continues today. The Himalayas are still rising at 10 millimeters per year as India continues pushing northward into Asia. This collision has also created the Tibetan Plateau, the world's largest and highest plateau, and continues to drive earthquake activity across a vast region from Turkey to Southeast Asia. 96. The mountain-moving impact. The Chicxulub asteroid impact instantly vaporized over 10,000 cubic kilometers of rock, while creating a crater 180 kilometers wide and 30 kilometers deep, fundamentally altering the geology of an entire region. The scale of excavation achieved by the Chicxulub impact is almost incomprehensible. The asteroid instantly removed a volume of rock equivalent to several mountain ranges, hurling the vaporized material into space while creating a hole in the Earth's crust deeper than Mount Everest is tall. The impact occurred in shallow tropical seas, which amplified the destruction. The asteroid not only vaporized rock, but also instantly converted massive amounts of seawater into superheated steam. The explosion threw debris across the entire planet, with impact ejecta found in rock layers on every continent. The crater structure that remains today is largely hidden beneath younger sediments, but geophysical surveys reveal a complex multi-ring basin with features that dwarf any impact crater on Earth's surface. The central peak ring alone is larger than many major cities, while the outer rim extends across an area larger than some small countries. 97. The 15-year nuclear winter. The Chicxulub impact threw so much debris into the atmosphere that it remained suspended for 15 years, creating a prolonged global winter that collapsed photosynthesis-based ecosystems worldwide. The impact didn't just kill through the initial explosion. It created environmental conditions that persisted for over a decade. The massive amounts of pulverized rock, vaporized seawater, and impact debris formed a global dust cloud that blocked sunlight more effectively than any volcanic eruption in Earth's history. Without adequate sunlight, photosynthesis essentially stopped across most of the planet. Plants died back, disrupting food webs from the bottom up. Herbivorous dinosaurs starved as vegetation disappeared, while carnivorous species followed as their prey populations collapsed. Only organisms that could survive without fresh plant production, decomposers, scavengers, and animals with stored energy reserves, had any chance of survival. The 15-year duration meant that the environmental crisis lasted longer than most ecosystem recovery cycles. Even if some organisms survived the initial impact and first year of darkness, they faced over a decade of degraded environmental conditions that prevented normal ecosystem functioning from resuming. 98. The supercontinent cycle. Over the past 3 billion years, Earth's continents have assembled into massive supercontinents at least 5 to 6 times, with individual supercontinents containing up to 75% of all continental crust before breaking apart and reassembling in new configurations. The supercontinent cycle represents one of the most fundamental patterns in Earth's geological history. Every 400 to 600 million years, the planet's continental masses converge into a single massive landmass, then gradually break apart and disperse before eventually reassembling again in a completely different configuration. Each supercontinent assembly and breakup event dramatically reorganizes global geography, climate, and ocean circulation patterns. When continents are assembled into supercontinents, vast interior regions become extremely arid and continental, while ocean circulation is simplified into a few major current systems. During breakup phases, new ocean basins form while continental fragments create more complex coastlines and climate patterns. The most recent supercontinent, Pangaea, broke apart 175 to 200 million years ago, creating the Atlantic Ocean and gradually moving continents toward their current positions. But the cycle continues. Plate tectonics models predict that the continents will begin converging again within the next 200 to 300 million years, eventually forming a new supercontinent with a completely different configuration. 99. The Great Freeze Trigger. The breakup of the supercontinent Rodinia 750 million years ago triggered the most extreme climate event in Earth's history. The snowball Earth glaciations that turned the entire planet into a frozen ice ball. Rodinia's breakup created massive environmental changes that pushed Earth's climate system past a critical tipping point. As the supercontinent fragmented, new coastlines and shallow seas increased chemical weathering rates, pulling CO2 out of the atmosphere faster than volcanic activity could replace it. The result was a runaway cooling effect that plunged the planet into the most severe ice age in its history. The snowball Earth events that followed Rodinia's breakup were so extreme, they nearly ended complex life before it had a chance to begin. For up to 10 million years at a time, ice covered the entire planet from pole to equator, creating conditions so harsh that only the most extreme environments could support any form of life. Paradoxically, these extreme glaciations may have been necessary for the evolution of complex life. The environmental stress and isolation created by global glaciation may have driven evolutionary innovations that led to the development of multicellular organisms and eventually to the Cambrian explosion of animal diversity. 100. The toxic atmosphere. During the Carboniferous period, atmospheric oxygen levels reached 35%. Concentrations that would cause oxygen poisoning and potentially fatal lung damage in modern humans. Breathing Carboniferous air would be like living in an oxygen-enriched environment that would quickly become toxic to human physiology. Prolonged exposure to 35% oxygen causes severe lung inflammation, central nervous system effects, and cellular damage from oxidative stress. What was life-giving for Carboniferous organisms would be lethal poison for modern animals. The hyperoxic atmosphere was created by the massive forests of primitive trees that pumped oxygen into the air faster than natural processes could remove it. These early trees had evolved wood and bark, but not efficient decomposition mechanisms, so dead plant material accumulated rather than rotting, removing carbon from the atmosphere while leaving excess oxygen behind. The high oxygen levels created a world of giants, but also a world of constant fire danger. Wildfires burned hotter and more intensely than anything in modern experience, capable of consuming entire forest systems in massive conflagrations that reshaped landscapes. The combination of giant insects and frequent massive fires created ecosystems unlike anything that exists today. 101. The Green Death Zones. During multiple periods in Earth's history, euxinic oceans covered vast areas with hydrogen sulfide-rich waters that were bright green in color and toxic to complex life, creating dead zones thousands of times larger than any modern ocean pollution. These weren't minor pollution events. They were complete transformations of ocean chemistry that turned vast areas of the sea into toxic wastelands. The hydrogen sulfide concentrations were so high that the water literally turned green from sulfur compounds, while the toxic conditions killed virtually all complex marine life across areas larger than entire continents. Euxinic conditions developed when ocean circulation broke down and deep waters became depleted of oxygen. Bacteria that thrive in oxygen-free environments began producing hydrogen sulfide as a waste product, creating a positive feedback loop that spread toxic conditions across entire ocean basins. These toxic oceans were visible from space, bright green patches that marked areas where normal marine ecosystems had collapsed into bacterial-dominated poison zones. The conditions were so extreme that they may have contributed to mass extinction events by eliminating marine food webs and releasing toxic gases into the atmosphere. 102. Life in battery acid. Around hydrothermal vents at crushing ocean depths, chemosynthetic bacteria thrive in environments more acidic than car battery fluid, while enduring pressures that would instantly crush any complex organism and temperatures that approach boiling. These extreme environments represent some of the most hostile conditions on Earth, yet they support thriving ecosystems based entirely on chemical energy rather than sunlight. The bacteria that form the base of these food webs can survive pH levels below 1, more acidic than stomach acid, while processing toxic heavy metals that would kill any surface organism instantly. The pressure at these depths exceeds 200 times atmospheric pressure, equivalent to having a large building sitting on every square inch of surface area. The temperature variations are equally extreme, with scalding water emerging from vents at over 400 degrees Celsius, while surrounding seawater remains near freezing. These vent ecosystems may represent the conditions where life first evolved on Earth, and they provide insights into how life might exist on other planets with extreme conditions. The bacteria that thrive in these environments have evolved biochemical pathways that have no equivalent in surface life, essentially representing alien biology on our own planet. 103. Racing toward the sixth extinction. Current extinction rates are 1,000 to 10,000 times higher than natural background rates, potentially marking the beginning of the sixth mass extinction, the first in Earth's history caused by a single species. Modern extinction rates are accelerating beyond anything in the geological record except during the Big Five mass extinction events. Species are disappearing so rapidly that Earth may be approaching the threshold for a mass extinction event comparable to those that reshaped life in the past. What makes the current extinction crisis unique is its cause. For the first time in Earth's history, a single species, humans, has gained the power to trigger global environmental changes comparable to asteroid impacts or massive volcanic eruptions. Human activities are simultaneously altering climate, ocean chemistry, habitat distribution, and ecosystem function at rates that exceed most species' ability to adapt. The current crisis differs from past mass extinctions in its speed and geographic scope. While previous extinctions were often regional events that spread gradually, human impacts are occurring simultaneously across all continents and marine environments, leaving few refuges where species can survive and recover. 104. The Age of Human Power. We are living in one of the most extraordinary periods in Earth's history, a time when a single species has gained the power to rival the great geological forces that shaped our planet's past. Human impacts on Earth systems now operate at scales comparable to the natural forces that have shaped the planet for billions of years. We move more rock and sediment than all rivers combined, alter atmospheric chemistry faster than most volcanic events, and change species distributions more rapidly than most climate changes. This represents a fundamental transition in how Earth systems operate. For the first time in the planet's 46 billion-year history, biological activity is driving changes in geology, atmosphere, and ocean chemistry at rates that exceed natural variability. We have become a geological force equivalent to tectonics, volcanism, or asteroid impacts. The recognition of this transition has led scientists to propose that we have entered a new geological epoch, the Anthropocene, defined by human dominance of Earth systems. Whether this epoch leads to continued prosperity or environmental collapse depends on decisions being made today by the first species in Earth's history capable of consciously directing its own evolutionary future. 105. The Living Laboratory. The story of prehistoric Earth serves as both inspiration and warning, proof that life can survive the most extreme conditions imaginable, but also evidence that the comfortable, stable world we know is neither permanent nor guaranteed. Earth's 46 billion-year history reveals a planet of constant change, where stability is the exception rather than the rule. Life has survived global freezing, planetary heating, atmospheric poisoning, asteroid impacts, and volcanic catastrophes that dwarf any modern environmental concerns. Yet these same events also eliminated up to 96% of species, showing that survival is never guaranteed. The geological record provides a vast library of natural experiments showing how life responds to environmental change. These ancient case studies offer crucial insights for understanding how modern ecosystems might respond to current environmental changes, while also revealing the ultimate resilience and adaptability of life itself. Perhaps most importantly, prehistoric Earth reminds us that we are part of an ongoing story that began billions of years ago and will continue long after human civilization. Understanding this deep history provides perspective on our current environmental challenges, while inspiring both humility about our place in Earth's story and confidence in life's ultimate ability to adapt and persist through even the most dramatic changes.